Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and the universe slows down just enough for us to wander through it without needing a map or a deadline. Tonight we're stepping into a question that sounds simple at first, but grows larger the longer you hold it in your mind, like a thought that keeps stretching as you try to wrap your arms around it. What is the largest object ever found in the universe? Not the brightest, not the oldest, not the most mysterious, but the biggest. The one that claims the most space, gathers the most matter, and quietly reminds us how small even our biggest ideas can be when set against the full scale of reality. Before we begin drifting outward, let me ask you something gentle and grounding. Where are you listening from right now? A bedroom, a couch, a quiet bus seat, or maybe a darkened room where the world has finally gone quiet? And what time is it in your part of the world? Somewhere the sun is rising. Somewhere else it is sinking below the horizon. And here we are, meeting in this small pocket of shared attention, about to think about things so large they make the idea of a horizon feel almost quaint. If you find this little journey calming, or if it gives you a sense of peace that comes from looking up instead of in, I'd be grateful if you gave the video a like, maybe even subscribed. It helps this slow, thoughtful corner of the internet reach others who might need a place to rest their minds for a while. And now, with nothing urgent to do and nowhere in particular to be, let's begin. When we ask about the largest object in the universe, it helps to pause for a moment and consider what we usually mean by an object. On Earth, the word feels straightforward. A rock is an object. A building is an object. A mountain can be treated as an object if you step back far enough. Each of these things has a shape, a boundary, and a clear sense of where it begins and ends. You can point to it. You can walk around it. You can say, this is here and that is over there. But the universe does not always cooperate with our need for clean edges and tidy categories. Out in space, matter does not always gather into neat, self-contained packages. Gravity stretches things. Motion blurs boundaries. Light takes time to travel, which means that when we look at something far away, we are not seeing it as it is right now, but as it was long ago, sometimes before Earth even existed. So when physicists talk about large objects on a cosmic scale, they often mean something a little different than what we mean in everyday life. Instead of a solid thing you could, at least in theory, touch or walk around, they mean a structure. A region of space where matter is more concentrated than its surroundings. A pattern shaped by gravity, expansion and time. At the smallest end of this scale, you have particles, tiny points of mass and energy, that behave more like probabilities than little solid beads. These gather into atoms, which gather into molecules, which gather into dust, rocks, planets and stars. Each step up in size is guided by a balance of forces. Gravity pulls things together. Heat and motion try to push them apart. Over billions of years, this quiet tug-of-war builds larger and larger structures. Stars, for example, are not just balls of glowing gas. They are ongoing negotiations between gravity and nuclear fusion. Gravity wants to collapse the star inward, making it smaller and denser. Fusion in the core releases energy, which pushes outward, trying to make the star expand. The size of a star is the result of this constant back and forth, a kind of physical conversation that can last for millions or billions of years. Now imagine taking not just one star, but hundreds of billions of them, along with clouds of gas, dust, and something we cannot see at all but know is there, dark matter. Let gravity begin the same process on this much larger scale. The result is a galaxy, a rotating system of stars and material held together by a massive, invisible gravitational framework. Our home, the Milky Way, is already so large that light takes about 100,000 years to cross from one side to the other. If you could travel at the speed of light, which nothing with mass can actually do, you would need 100 millennia just to go from one edge of our galaxy to the other. And the Milky Way is not especially large by cosmic standards. It is a fairly average spiral galaxy, one of hundreds of billions in the observable universe. At this point, it might already feel like we have reached a natural limit. A galaxy seems big enough to earn the title of largest object. It contains more stars than there are grains of sand on many of the Earth's beaches. It holds enough mass to shape the motion of smaller galaxies nearby. It can dominate its region of space for millions of light years in every direction. But gravity, patient and persistent, does not stop there. Galaxies are not evenly scattered through space like sprinkles on a cake. They tend to gather in groups. These groups form because each galaxy's mass, and the mass of the dark matter surrounding it, pulls on its neighbours. Over time, this attraction draws them together into collections called galaxy groups and galaxy clusters. A galaxy cluster can contain hundreds or even thousands of galaxies, all orbiting a common centre of mass. The space between them is not empty. It is filled with extremely hot gas, heated to millions of degrees as it falls into the cluster's deep gravitational well. This gas glows in X-rays, which is one of the ways astronomers detect and study these enormous structures. If you could stand somewhere inside a galaxy cluster, though standing is a bit of a stretch in the vacuum of space, you would see galaxies drifting past each other like slow-moving cities of light. The scale is hard to express in familiar terms. The distances between galaxies in a cluster are so vast that even at light speed, it would take millions of years to travel from one to the next. Yet, in cosmic terms, they are close enough to be considered part of the same system. For a long time, galaxy clusters were thought to be about as big as gravity could build. They were considered the largest objects in the universe that were truly bound together, meaning that their parts were held in a stable relationship by their mutual gravitational pull. Then, as telescopes improved and surveys of the sky became more detailed, something even larger began to emerge from the data. Astronomers started to notice that galaxy clusters themselves were not randomly placed. When they mapped the positions of thousands and then millions of galaxies, a pattern appeared. It looked less like a smooth, even spread, and more like a vast three-dimensional web. In this cosmic web, galaxies and clusters trace out long filaments, thin in one dimension and incredibly extended in another. Between these filaments are enormous voids, regions of space with very few galaxies at all. The whole structure resembles a sponge or a network of interconnected threads stretching across the observable universe. This pattern is not accidental. It is the result of how matter responded to tiny differences in density in the early universe. Shortly after the Big Bang, the universe was almost perfectly uniform, but not quite. Some regions were slightly denser than others. Over billions of years, gravity amplified these small differences. Denser regions pulled in more matter, becoming even denser. Less dense regions lost matter, becoming emptier. Dark matter plays a central role in this process. Unlike normal matter, dark matter does not interact with light, so we cannot see it directly. But it does interact with gravity, and it makes up most of the mass in the universe. It forms the invisible scaffolding on which galaxies and clusters are built. The filaments of the cosmic web are, in a sense, outlines drawn by dark matter, with visible galaxies lighting up the structure like lanterns along a hidden frame. Within this web, astronomers began to identify structures so large that they challenged previous ideas about how big a single object could be. These are called superclusters, and even larger formations sometimes referred to as great walls. A supercluster is a massive region of space containing multiple galaxy clusters and groups, all loosely connected by gravity and the underlying dark matter framework. Unlike a galaxy cluster, a supercluster is not always fully bound. Its parts may be slowly drifting apart due to the overall expansion of the universe, even as some regions within it remain gravitationally linked. One of the most famous examples is the Laniakea supercluster, which includes the Milky Way and tens of thousands of other galaxies. Laniakea spans about 500 million light-years and contains the mass of roughly 100,000 Milky Way-sized galaxies. When scientists mapped the motion of galaxies in this region, they found that many of them were flowing toward a common gravitational centre, a kind of cosmic valley in the landscape of space-time. But even Laniakea is not the end of the story. Beyond superclusters, astronomers have found structures that stretch across more than 1 billion light-years. These are vast chains of galaxies and clusters linked along filaments, forming walls, arcs, and sheets in the cosmic web. They are not solid objects in the traditional sense. You could not draw a sharp line around them and say, this is where it ends. Instead, they fade gradually into the surrounding web, becoming less dense, less defined, but still part of a larger pattern. One of the most studied of these enormous structures is known as the Sloan Great Wall. It was discovered in the early 2000s using data from the Sloan Digital Sky Survey, a project that mapped the positions and distances of millions of galaxies. The Sloan Great Wall is about 1.4 billion light-years long. To put that in perspective, light has been travelling since before the first complex life appeared on Earth, and it still would not have crossed the entire length of this structure. At the time of its discovery, it was considered the largest known structure in the universe. It challenged cosmologists because it seemed to approach the theoretical limit of how large a structure could be if the universe were truly uniform on the larger scales, as predicted by the Standard Model of Cosmology. The idea behind that model is that while the universe looks clumpy and structured on small and medium scales, when you zoom out far enough, it should look smooth and uniform, like looking at a forest from up close, where you see individual trees, and then from far away, where you just see a green blur. Structures like the Sloan Great Wall sit near the boundary between these two regimes, where the universe transitions from being obviously structured to being statistically smooth. As surveys expanded and data improved, even larger features were reported. Some studies have suggested the existence of structures like the Hercules Corona Borealis Great Wall, which may span over 10 billion light-years, though its exact nature and even its status as a single coherent structure are still debated. And this brings us back to our original question, now wrapped in layers of complexity. What is the largest object ever found in the universe? For now, it's enough to sit with the idea that the universe does not organise itself into neat, isolated pieces. It builds in layers. Particles become atoms. Atoms become stars. Stars become galaxies. Galaxies become clusters. Clusters trace out filaments that span billions of light-years. At each step, gravity and expansion work together, shaping a structure that is both connected and constantly changing. As you rest here, thinking about these immense scales, notice how your own sense of size and distance begins to soften. The room you are in, the building around you, the city, the planet, all of it becomes part of a much longer chain of structures, nested inside one another like a series of quiet, patient boxes. Before we can move any farther into questions of size and scale, it helps to slow down and look carefully at the word that seems so simple on the surface, yet becomes surprisingly slippery the moment you place it into a cosmic setting. When physicists say object, they are not always talking about something you could point to, pick up, or walk around. In everyday life, an object is a thing with a clear outline. A chair has edges, a cup has a rim, a building has walls. You can draw a line around it and say, this is where it ends, and everything else begins. Out in the universe, that kind of clarity is rare. Matter does not sit still. Space itself is not a rigid stage. Everything is in motion, pulled, pushed, stretched, and shaped by gravity, energy, and the steady expansion of the cosmos. So when scientists talk about an object on a large scale, what they often mean is not a solid thing with a sharp boundary, but a region of space where something interesting is happening in a consistent and recognizable way. Think about a cloud in the sky. From a distance, it looks like a single, unified shape. You might point to it and say, that is a cloud. But if you were able to drift inside it, you would not find a clear wall or surface. The cloud fades gradually into the surrounding air. Its edges are soft, defined more by changes in density than by any solid barrier. In many ways, cosmic objects are like this. They are defined by patterns, not by walls. In physics, an object is often described in terms of its physical properties: mass, energy, motion, and the forces acting on it. On small scales, these properties can be tied to something compact and well-defined, like a planet or a star. A planet has a mass you can calculate, a radius you can measure, and an orbit you can track. A star has a core, a surface, and a predictable way it shines. But as you move up the ladder of size, things begin to blur. Take a galaxy. At first glance, it seems like a clear example of a cosmic object. It has a centre, a general shape, and a collection of stars that move together. You can map its rotation. You can estimate its total mass. You can even draw a rough outline around where most of its visible light comes from. Then you look a little closer. Galaxies are surrounded by vast halos of dark matter that extend far beyond the region where most of the stars live. This dark matter does not emit light, so you cannot see its edges directly. You infer its presence from the way stars and gas move under its gravitational influence. The galaxy, in this sense, is much larger than what your eyes or telescopes first reveal. So where does the galaxy end? At the last visible star, at the edge of the dark matter halo, or somewhere in between? Physicists answer this kind of question by choosing a definition that fits the problem they are trying to solve. If they are studying how stars form, they might focus on the bright, dense central region of a galaxy. If they are studying how galaxies interact with each other, they might include the dark matter halo, because that is what largely determines how two galaxies pull on one another. This flexibility is a key part of how science works. An object is not always a single, absolute thing. It is often a useful way of grouping parts of the universe together so they can be studied as a system. A system is another word physicists use a lot. A system is a collection of components that interact with each other in some meaningful way. A solar system is a system because the planets, moons and the star are all bound together by gravity and influence each other's motion. A galaxy is a system because its stars, gas, dust and dark matter move in response to a shared gravitational field. On larger scales, clusters of galaxies become systems, and even the filaments of the cosmic web can be treated as systems when scientists model how matter flows through the universe. So when someone asks about the largest object in the universe, one of the first things a physicist quietly asks themselves is, what kind of system are we talking about? Another way physicists define objects is by looking at whether something is gravitationally bound. To be gravitationally bound means that the parts of a system are held together strongly enough by gravity that despite the expansion of the universe, they will remain connected over time. A planet is gravitationally bound to its star. The star is gravitationally bound to its galaxy. A galaxy is often gravitationally bound to a cluster of other galaxies. But as you go to larger and larger scales, the expansion of the universe begins to compete with gravity more effectively. The universe is not just sitting there. Space itself is stretching. This means that, on very large scales, distant galaxies are moving away from each other, not because they are flying through space, but because the space between them is growing. If gravity between two regions of matter is strong enough, it can overcome this expansion and keep them together. If it is not, the expansion wins, and those regions drift apart over cosmic time. This leads to a natural dividing line. A gravitationally bound structure can be considered a single object in a meaningful physical sense, because its parts share a common future. They will continue to interact, orbit, and influence each other. An unbound structure, on the other hand, may look connected in a snapshot of the universe, but its pieces are slowly separating, destined to become isolated from one another as billions of years pass. This distinction is one reason why some scientists hesitate to call the very largest cosmic structures true objects. A The Great Wall of Galaxies might stretch across billions of light years, but different parts of it may not be gravitationally bound to each other. Over time, the expansion of the universe will pull those regions farther and farther apart, until any sense of unity becomes more a matter of historical connection than physical interaction. Still, even this boundary is not perfectly sharp. Gravity works over long distances, and dark matter adds extra mass and pull in ways that are not always easy to map. So, whether a structure is fully bound, or only loosely connected, can depend on how carefully you measure it, and how far into the future you try to predict its behaviour. Another way physicists think about objects is through the idea of coherence. A coherent object is one that behaves in a coordinated way. Its parts move together, respond together to forces, or share a common pattern of motion. A rotating galaxy is coherent. Its stars, while each following their own paths, participate in an overall rotation around the centre. A cluster of galaxies can be coherent if its members orbit a shared centre of mass, even if those orbits take billions of years to complete. On even larger scales, coherence becomes harder to define. Filaments of galaxies may align along similar directions, shaped by the same underlying dark matter structures, but the galaxies within them may not be moving in any strongly coordinated way. They share a location within the cosmic web, but not necessarily a shared motion or destiny. This brings us to another subtle point. In physics, an object does not have to be a thing. It can be a process. A storm on Earth is often treated as an object for the purpose of study. It has a size, a shape, and a path. But a storm is really a pattern of moving air, water, and energy. The molecules that make it up are constantly changing. New air flows in, old air flows out. The storm persists not because it is made of the same material over time, but because the pattern continues. In a similar way, some of the largest structures in the universe are better thought of as persistent patterns in the distribution of matter rather than as fixed collections of the same particles. The cosmic web itself is a pattern. Galaxies move along filaments. Clusters grow and merge. Voids expand. Over billions of years, the specific galaxies in a given region can change, but the overall structure can remain recognizable. So when we point to something like a supercluster or a great wall and call it an object, what we really mean is that it is a stable, large-scale pattern in how matter is arranged. This perspective becomes even more important when you consider how we actually observe the universe. We do not see things as they are now. We see them as they were when the light left them. For nearby stars, that delay is a few years. For distant galaxies, it can be billions of years. This means that a single image of a very large structure is actually a kind of time collage. The near side is being seen at a more recent moment in cosmic history than the far side. Imagine trying to take a photograph of a parade that is miles long, but your camera takes several hours to record the image from one end to the other. The front of the parade in your picture would show people at a different moment than the back. That is roughly what happens when we observe structures that span hundreds of millions or billions of light years. So when physicists define an object on these scales, they're often working with something that is spread out not just in space, but in time. The object, in a sense, is four-dimensional. It has a shape in space and a history through time. This leads to another useful concept called a world line, or for extended objects, a world tube. These are ways of describing how an object exists and moves through space-time, the combined fabric of space and time. For a small object, like a particle, its world line is a thin thread tracing its path through the universe. For a galaxy or a cluster, its world tube is a thick, sprawling shape that represents the evolving positions of all its parts. Thinking this way, the question of where an object begins and ends becomes even more flexible. You can define it at a particular moment, or you can define it as a continuous presence across billions of years. Another layer of complexity comes from how physicists categorize matter and energy. On cosmic scales, much of what holds structures together is not the ordinary matter that makes up stars, planets, and people. It is dark matter which interacts through gravity but not through light. Because it does not shine, reflect or absorb light in a way we can easily detect. We often only know where it is by observing its effects on visible matter. This means that the visible part of an object can be just the tip of a much larger invisible structure. A galaxy might look like a glowing disk or an elegant spiral, but most of its mass is actually in a dark matter halo that extends far beyond the visible stars. So when a physicist talks about the size of a galaxy, they might mean the size of the bright part, the size of the dark matter halo, or the size of the region over which its gravity dominates. Each of these is a valid definition, depending on what you're trying to understand. The same is true for larger structures. A galaxy cluster's visible galaxies might occupy a certain region, but its gravitational influence extends much farther, shaping the motion of gas and smaller groups of galaxies well beyond the cluster's bright core. There is also a statistical way of thinking about objects in the universe. On the larger scales, cosmologists often describe the universe in terms of averages. They talk about the average density of matter, the average temperature of cosmic radiation, the average rate of expansion. In this view, individual objects become less important than the overall pattern. But even here, objects still appear as deviations from the average. A galaxy is a region where the density of matter is much higher than the cosmic mean. A void is a region where it is much lower. The larger structures are simply the biggest and most extended of these deviations. So an object in this sense is a place where the universe is doing something different from what it is doing, on average, elsewhere. This way of thinking helps explain why the question of the largest object is not just about measuring a size with a ruler. It is about deciding what counts as a meaningful difference, a meaningful pattern, a meaningful system. Is a filament of galaxies an object because it stands out from the surrounding voids? Is a supercluster an object because its galaxies share a general flow toward a common region of space? Is the observable universe itself an object because it represents the region where light has had time to reach us since the beginning of cosmic expansion? Each of these answers tells you something different about what you value in a definition. There is also a human element to all of this. We like to name things. We like to draw boundaries. We like to say, this is one thing and that is another. The universe, however, often resists these tidy labels. It prefers gradients to edges, flows to walls, connections to separations. Physicists, aware of this, tend to be careful in their language. They might talk about a structure being identified rather than found, because it's often a matter of interpreting data and deciding that a certain pattern is significant enough to be given a name. For example, when astronomers map millions of galaxies and see a long chain of higher density regions, they have to decide whether this chain is a single, coherent structure or just a chance alignment of smaller ones. Statistical tests are used to estimate how likely it is that such a pattern would appear randomly. If the probability is low enough, the structure earns a place in the catalogue of known cosmic features. So in a very real sense, the largest objects in the universe are not just discovered, they are defined. They emerge from a conversation between data, theory, and human judgment. As you sit with this idea, it might be interesting to notice how it mirrors the way we define objects in everyday life. A river is an object, even though the water in it is constantly changing. A city is an object, even though its buildings rise and fall, and its people come and go. What makes these things objects is not that they are made of the same material over time, but that they maintain a recognizable pattern. The universe, on its grandest scales, works in much the same way. Its largest objects are patterns in the distribution and motion of matter and energy, shaped by gravity, expansion, and the deep history of cosmic evolution. How do physicists and astronomers actually measure these enormous patterns? How do they turn faint points of light in a telescope into maps of structures that span billions of light years? And how do they decide with any confidence at all that one of these vast subtle shapes is bigger than all the rest? Let the idea of an object soften and expand in your mind, not as a solid thing with a hard edge, but as a region of connection, a shared motion, a persistent pattern in a universe that is always, quietly, in the process of becoming something new. In the universe, distance is never just about space. It is also about time. When physicists and astronomers look outward, they are not peering across a vast silent stage that exists only in the present. They are looking into a layered record of history, where every point of light carries with it a story about when and where it began its journey. So when we talk about measuring the universe, we are really talking about learning how to read light as both a ruler and a clock at the same time. Here on Earth, measuring distance feels simple. You can use a tape measure, a ruler, a laser rangefinder, or even your own footsteps. You and the thing you are measuring exist in the same moment. There is no meaningful delay between when you look at something and when you see it. Light moves so quickly over everyday distances that it might as well be instant. But space does not play by those rules. Light, fast as it is, still has a finite speed. It travels at about 300,000 kilometers per second, which sounds unimaginably quick until you realize how unimaginably large the universe is. Even at that speed, light takes a little over a second to reach Earth from the Moon. It takes about 8 minutes to reach us from the Sun. It takes years to reach us from the nearest stars, and billions of years to reach us from the most distant galaxies we can observe. This simple fact changes everything about how we measure the cosmos. When you look at the night sky, you are not seeing things as they are now. You're seeing them as they were when their light began its journey toward you. The moon you see is about 1 second in the past. The sun is 8 minutes in the past. The bright star Sirius is about 8 years in the past. A distant galaxy might be billions of years in the past. So the universe, as we observe it, is a layered structure of different moments in time, all projected onto the same dome of the sky. Near and far are also now and then. This is the foundation of cosmic measurement. If you can figure out how long light has been travelling, you can figure out how far away its source is. Time becomes a ruler. The most basic unit that captures this idea is the light year. A light year is not a time, despite the name. It is a distance. It is the distance light travels in 1 year, which is about 9.46 trillion kilometres. It is a number so large that it is almost useless for everyday purposes, but incredibly convenient for talking about stars and galaxies. If a star is 10 light years away, it means the light you see from it tonight left that star 10 years ago. If a galaxy is 1 billion light years away, you are seeing it as it was 1 billion years in the past. But how do scientists actually figure out those numbers in the first place? How do they know how long light has been travelling when they receive it? The answer is that they build a kind of a ladder, where each step helps measure a certain range of distances, and each step is calibrated using the one below it. This is often called the cosmic distance ladder. At the closest distances within our solar system, astronomers use geometry. One of the simplest and most powerful tools is parallax. If you hold your thumb out in front of you and close one eye then the other, your thumb appears to shift against the background. That shift happens because your eyes are in slightly different positions, giving you 2 different perspectives. Astronomers use the same idea with Earth's orbit. They observe a nearby star, then wait 6 months and observe it again when Earth is on the opposite side of its orbit. The star appears to shift slightly against the background of more distant stars. By measuring that tiny angle and knowing the size of Earth's orbit, they can use simple trigonometry to calculate the star's distance. This method works well for stars within a few thousand light years. Beyond that, the shift becomes too small to measure accurately, even with powerful telescopes. So astronomers move up to the next rung on the ladder using objects whose intrinsic brightness is known. If you know how bright something really is, and you measure how bright it appears from Earth, you can calculate how far away it must be. This is similar to seeing a street lamp at night. If you know how bright street lamps usually are, you can estimate how far away one is based on how dim it looks. One of the most important types of these objects is called a Cepheid variable star. These stars pulse in brightness in a very regular way. The key discovery made in the early 20th century was that the period of a Cepheid's pulsing is directly related to its true brightness. Measure how long it takes to brighten and dim, and you can determine how luminous it really is. Once you know that, you compare it to how bright it appears from Earth, and the difference tells you the distance. Cepheids can be seen in nearby galaxies, which makes them a bridge between measuring stars in our own galaxy and measuring other galaxies. Beyond that, astronomers use even brighter objects, such as certain types of supernovae. A particular kind, known as type Ia supernovae, has a very consistent peak brightness. These are explosions of white dwarf stars that reach nearly the same energy output every time. When one of these goes off in a distant galaxy, it can be seen across vast stretches of space. By measuring how bright the supernova appears and comparing it to how bright it should be, scientists can estimate the distance to its host galaxy, even when that galaxy is billions of light years away. So far, this all sounds like measuring distance, but now time enters in a second, deeper way. As the universe expands, it stretches the light travelling through it. This stretching shifts the light toward the red end of the spectrum, a phenomenon known as redshift. The more the universe has expanded while the light was on its way to us, the more stretched, or redshifted, that light becomes. By analysing the spectrum of light from a galaxy, astronomers can measure how much it has been redshifted. That redshift tells them how fast the galaxy is moving away from us due to cosmic expansion. And because the rate of expansion is related to time, this also gives a clue about how long the light has been travelling. So now light is doing double duty. Its brightness helps measure distance. Its colour shift helps measure speed and indirectly time. This combination allows scientists to build a three-dimensional time-aware map of the universe. They can place galaxies not just in a direction on the sky, but at a distance and at a moment in cosmic history. When astronomers conduct large surveys, mapping millions of galaxies, they use these techniques to create vast data sets. Each galaxy becomes a point in a kind of four-dimensional space, with coordinates for its position and its redshift, which corresponds to its distance and the age of the universe when its light was emitted. From this, the cosmic web begins to appear. Filaments, clusters, and voids emerge, not because someone drew them in, but because the data itself reveals where matter is gathered and where it is scarce. Now consider what this means for identifying the larger structures. A structure that spans 1 billion light-years in space also spans a significant amount of time in observation. The light from the near side of that structure might have been travelling for, say, 1 billion years. The light from the far side might have been travelling for 2 billion years. So when you see the whole thing at once, you are seeing different parts of it at different stages of cosmic history. This makes defining its size and shape more complex. You're not looking at a single frozen object. You're looking at a long, evolving process stretched across time and space. Physicists deal with this by choosing a reference frame, a way of slicing the universe into moments. Often, they use what is called co-moving coordinates. These are coordinates that expand along with the universe. Instead of tracking how far apart things are right now, they track how far apart they would be if you could somehow pause the expansion and measure the distances in a consistent way. Using these coordinates, astronomers can talk about the true size of a structure in a way that is not constantly changing as the universe expands. It is a bit like drawing a grid on a balloon and then inflating the balloon. The grid stretches, but the pattern stays the same. Co-moving coordinates track the pattern, not the stretched distances. Another layer of measurement comes from the cosmic microwave background, often called the afterglow of the Big Bang. This is a faint, uniform radiation that fills the entire universe. It was released when the universe was about 380,000 years old, when matter and radiation decoupled and light was finally able to travel freely through space. This background radiation is incredibly smooth, but it has tiny variations in temperature and density. These variations represent the seeds of all the structures we see today. By studying them, physicists can learn about the initial conditions of the universe and how matter began to clump together. The cosmic microwave background provides a kind of universal reference scale. It allows scientists to calibrate their measurements of expansion, distance, and structure. It is like having a faint ancient grid drawn across the entire sky, against which everything else can be compared. Now think about what it takes to turn all this light into a map. Telescopes collect photons, tiny packets of light that have been travelling for millions or billions of years. These photons hit a detector, producing a small electrical signal. That signal is recorded as a pixel in an image or a data point in a spectrum. One photon does not tell you much, but when you collect millions or billions of them, patterns begin to emerge. Astronomers then apply models of how light behaves, how stars and galaxies emit light, how dust absorbs and scatters it, and how the universe expands. They use these models to translate raw data into estimates of distance, mass, and motion. There is always uncertainty. Every measurement has an error bar, a range of possible values. When dealing with the largest structures in the universe, those uncertainties can be enormous. A small percentage error in distance can translate into hundreds of millions of light years. So when scientists say that one structure is larger than another, they're often making a statistical statement. Based on the best available data and models, this structure appears to span a greater region of space than that one, within certain margins of error. This is why debates about the largest object in the universe can last for years. New surveys bring in more data. New methods refine distance estimates. A structure that once seemed like a single, continuous feature might turn out to be several smaller ones aligned along our line of sight, or a region that seemed modest might reveal hidden extensions when more galaxies are mapped. There is also the challenge of selection. We can only measure what we can see. Faint galaxies are harder to detect at great distances. Dust can obscure parts of the sky. The limits of our instruments create a kind of cosmic horizon, beyond which our maps become less complete. This means that our picture of the largest structures is always provisional. It is the best we can do with the light that has reached us so far, and the tools we have built to capture it. Another subtlety comes from the fact that light does not always travel in a straight line. Massive objects like galaxies and clusters can bend space-time, causing light to follow curved paths. This effect, known as gravitational lensing, can magnify, distort, or even create multiple images of distant galaxies. Astronomers use lensing both as a complication and as a tool. It can make it harder to interpret what you're seeing, but it can also reveal the presence of dark matter, because the amount of bending depends on the total mass of the lensing object, visible and invisible. By mapping how background galaxies are distorted across the sky, scientists can create maps of dark matter distribution. These maps often line up with the filaments and clusters of the cosmic web, providing another way to measure the size and shape of the larger structures. So measuring the universe is not a single technique, it is a tapestry of methods, all woven together. Geometry, brightness, colour, motion, background radiation, and gravitational effects all contribute to the final picture. At its heart, though, it all comes back to light and time. Every photon is a messenger from the past. It carries information about where it came from, what it passed through, and how the universe changed while it was on its way. By collecting and interpreting these messages, physicists turn the sky into a kind of historical record, a book written in wavelengths and travel times. And in that book, the largest objects in the universe appear not as isolated things, but as extended stories. They are chapters in the long narrative of how matter gathered, how gravity sculpted space, and how the universe grew from a nearly uniform beginning into a richly textured cosmic web. It might be comforting to think that even here, in a quiet room on a small planet, you are connected to this process. The light entering your eyes from a lamp or a screen has travelled only a short distance, but the same laws govern it as govern the light that has crossed billions of light years to reach a telescope. Let's take a moment to think about gravity not as something that makes your feet stay on the floor or keeps the moon circling the Earth. but as a quiet, persistent designer working on a scale so large that its projects take billions of years to take shape. In everyday life, gravity feels simple. Things fall down, water flows downhill. You feel a gentle, constant pull toward the ground. But in the universe at large, gravity is less like a single downward force and more like a network of invisible threads, connecting every piece of matter to every other, shaping where things gather and how they move across immense stretches of space. At its most basic level, gravity is a relationship between mass and distance. Anything with mass pulls on anything else with mass. The more mass something has, the stronger its pull. The farther apart two things are, the weaker that pull becomes. This idea, first written down clearly by Isaac Newton, works beautifully for most situations we encounter. It explains why planets orbit stars, why moons orbit planets, and why galaxies hold together instead of drifting apart like scattered sparks. But gravity does not stop working just because things are far away. Even across millions or billions of light years, its influence, though weakened, is still there. And over the vast timescales of cosmic history, even a very gentle pull can have dramatic effects. To see how gravity becomes an architect, it helps to go back to the early universe, long before there were stars, galaxies, or even atoms as we know them. Shortly after the Big Bang, the universe was hot, dense, and almost perfectly uniform. Matter and energy were spread out in a nearly even soup, but not quite. There were tiny variations in density, slight regions where there was a little more matter than average, and others where there was a little less. These differences were incredibly small, often only 1 part in 100,000. If you could have looked at the universe back then, it would have seemed smooth and featureless. But gravity noticed those differences. In regions that were just a bit denser, the gravitational pull was slightly stronger. That extra pull drew in more matter from the surrounding areas. As more matter gathered, the region became denser still, which made its gravity even stronger, which drew in even more matter. This is a feedback loop, slow and steady, playing out over hundreds of millions and then billions of years. Meanwhile, the less dense regions lost matter to their denser neighbours. They became emptier over time, forming the vast cosmic voids we see today. Enormous bubbles of space with very few galaxies inside them. So from these tiny, almost invisible differences in the early universe, gravity began to carve out a large-scale pattern. Dense regions became filaments and clusters. Empty regions became voids. The result, after enough time had passed, is the cosmic web, a vast network of matter stretching across the observable universe. This process is not dramatic in the way explosions or collisions are dramatic. It is patient. It is relentless. It is more like erosion shaping a landscape than like a hammer building a wall. Gravity works with what is already there, nudging matter along paths that slowly become more and more defined. Now, consider how this works on smaller scales. Take a cloud of gas and dust floating in space. On its own, it might seem stable. The particles within it are moving, bumping into each other, creating pressure that pushes outward. Gravity, meanwhile, is pulling everything inward. If the inward pull becomes slightly stronger than the outward pressure, the cloud begins to collapse. As it collapses, it heats up. The particles move faster, the pressure increases. Eventually, a balance can be reached where gravity pulls inward and pressure pushes outward with equal strength. At that point, you might get a stable structure like a star. So a star is, in a sense, a compromise between gravity and energy. Gravity wants to make it smaller and denser. Nuclear fusion in the core releases energy that wants to make it expand. The star's size, brightness, and lifespan are all determined by how this balance plays out. Scale this up, and you see the same story repeated. A galaxy forms when gravity pulls together vast numbers of stars, clouds of gas, and crucially, dark matter. The dark matter forms a large invisible halo that extends far beyond the visible part of the galaxy. This halo provides most of the gravitational pull that holds the galaxy together. Within that halo, ordinary matter cools and settles into rotating disks or spheroids, forming stars and planets. The shape of a galaxy, whether it becomes a graceful spiral or a more rounded elliptical form, depends on its history. Has it collided with other galaxies? Has it grown quietly by drawing in smaller neighbours? Has it been stretched or compressed by nearby massive structures? Each of these events is guided by gravity, but not in a simple one-on-one way. When two galaxies approach each other, their gravitational fields interact. Stars in one galaxy feel the pull of the other. Gas clouds are stretched into long tails. Dark matter halos overlap and merge. The result can be a slow, complex dance that lasts for hundreds of millions of years. Sometimes this dance ends in a merger, where two galaxies become one larger galaxy. Sometimes they pass by each other, altered but still separate. Either way, gravity leaves its mark on their structure. Now, step back again and look at clusters of galaxies. A galaxy cluster forms when multiple galaxies and groups of galaxies fall into a shared gravitational well. This well is mostly created by dark matter, which outweighs ordinary matter by a large factor. The dark matter gathers first, forming a deep basin in the gravitational landscape. Then, galaxies and gas fall into that basin. As gas falls in, it accelerates and heats up, reaching temperatures of millions of degrees. This hot gas fills the space between the galaxies in the cluster and can outweigh all the stars combined. It shines in X-rays, revealing the shape of the cluster's gravitational potential. Within this environment, galaxies move at speeds of hundreds or even thousands of kilometers per second. They can be stripped of their gas by the pressure of the hot cluster medium. Their star formation can be quenched. Their shapes can be distorted. All of this is gravity at work, not just holding things together, but actively reshaping them. And still, gravity does not stop at the edge of a cluster. Clusters themselves are connected by filaments, long strands of dark matter and gas that trace the paths along which matter flows. These filaments act like cosmic highways, guiding galaxies toward denser regions. Over time, smaller groups of galaxies travel along these filaments and are absorbed into clusters, making them grow larger and more massive. This is why the larger structures in the universe tend to form at the intersections of filaments. These are the nodes of the cosmic web, where matter has had the most time and opportunity to gather. If you could somehow watch the universe evolve in fast forward, you would see matter slowly streaming along these invisible paths, like water flowing along a network of rivers toward the deepest valleys. But there is another player in this story, one that complicates gravity's role as an architect. That player is the expansion of the universe. Since the Big Bang, space itself has been stretching. On very large scales, this stretching causes distant galaxies to move away from each other. The farther apart two galaxies are, the faster this expansion pushes them away. So gravity and expansion are in constant competition. On small scales, like within a solar system or a galaxy, gravity wins easily. The expansion of space is so weak there that it is completely overwhelmed by the gravitational pull of nearby mass. On intermediate scales, like within clusters and superclusters, the balance becomes more interesting. Some regions remain gravitationally bound. Others are just barely holding together. Some are slowly being pulled apart by expansion. On the very largest scales, expansion dominates. Regions of the universe that are far enough apart are effectively disconnected. No matter how long you wait, gravity will never be able to pull them back together, because the space between them is growing too quickly. This means that gravity's architectural reach has a limit. There is a maximum scale on which it can build coherent structures. Beyond that, the universe becomes more like a smooth, expanding field, with local patterns but no global unified form. Understanding where this limit lies is one of the reasons scientists care so much about the size of the largest cosmic structures. If they find something larger than what current theories predict should be possible, it can signal that our understanding of gravity expansion or the early universe needs to be revised. Now, let's bring dark matter back into the picture, because gravity alone does not tell the whole story unless you include it. Ordinary matter, the kind that makes up stars, planets and people, interacts with itself in many ways. It collides, sticks together, heats up, cools down and emits light. Dark matter, as far as we know, does none of these things. It does not collide in the same way. It does not radiate energy. It mostly just sits there and exerts gravitational pull. Because of this, dark matter began to form structures earlier than ordinary matter did. In the early universe, ordinary matter was coupled to radiation. It was hot and energetic, resisting collapse. Dark matter, on the other hand, could begin to clump under gravity almost immediately. So the first scaffolding of cosmic structure was built by dark matter. It formed a network of dense regions and filaments. Later, as the universe cooled, ordinary matter fell into this network, collecting in the gravitational wells created by the dark matter. This is why, when scientists map the distribution of galaxies, they often find that it traces out the same pattern as the distribution of dark matter inferred from gravitational lensing and other methods. The visible universe is, in a sense, painted onto an invisible framework. This framework is what allows gravity to build such large and complex structures. Without dark matter, the universe would look very different. Galaxies would be smaller. Clusters might not form at all. The cosmic web would be much less pronounced. So when we talk about gravity as the architect of cosmic structure, we're really talking about gravity working through both visible and invisible matter, shaping a universe that is only partly lit up. There is also a deeper layer to gravity, one that comes from Einstein's theory of general relativity. In this view, gravity is not just a force pulling objects together. It is a result of the curvature of space-time itself. Mass and energy tell space-time how to bend. Space-time tells mass and energy how to move. On small scales, this bending is subtle. On large scales, especially around massive objects like galaxy clusters, it becomes significant. Light travelling through these regions follows curved paths, creating the gravitational lensing effects we mentioned earlier. This bending of space-time also influences how structures grow. Regions of curved space-time act like basins guiding the motion of matter. Over time, these basins can deepen as more mass falls in, reinforcing the pattern. So gravity in this sense is not just pulling on matter, it is shaping the very stage on which matter moves. Another interesting aspect of gravity's role as an architect is that it builds hierarchically. Small structures form first, stars form within galaxies, galaxies form within groups, groups merge into clusters, clusters connect into superclusters and filaments. Each level is built from the merging and growth of the level below. This means that the largest structures in the universe are, in a way, the result of countless smaller events. Every star that formed, every galaxy that merged, every cluster that grew contributed a tiny piece to the final pattern. This hierarchical growth also means that the universe is still under construction. The largest structures we see today are not finished. They're still evolving. Galaxies are still falling into clusters. Filaments are still drawing in matter. Voids are still expanding. If you could wait long enough, you would see the cosmic web slowly change shape. Some filaments would thin out, some clusters would grow larger, some regions would become more isolated as expansion carries them beyond each other's reach. This brings us to an interesting point about the idea of the largest object. In a universe that is always changing, size is not a fixed property. A structure that is the largest today might not be the largest in the future. New connections might form, old ones might fade. So when we talk about gravity building the larger structures, we're talking about an ongoing process, not a finished result. It might be calming to think of gravity not as a harsh or violent force, but as a steady presence. It does not rush. It does not tire. It works quietly, shaping patterns over timescales that make human history look like a brief flicker. In the room where you are now, gravity is holding you in place. gently and consistently. On a scale far beyond what you can see, that same influence is guiding galaxies along invisible paths, drawing them into clusters, stretching filaments across billions of light years, and slowly, patiently, sketching the larger structures the universe has to offer. Let's shift our attention gently from the grand, sweeping motions of galaxies and filaments back down to the smallest ingredients of everything, because the story of size in the universe does not begin with stars or clusters. It begins with things so small that calling them things already stretches the imagination. And yet, from these nearly invisible beginnings, every planet, every mountain, every cloud of gas, and every great wall of galaxies eventually takes shape. At the most basic level, what we call matter is made of particles. Some of these, like electrons and quarks, are considered fundamental, meaning that as far as we know, they are not made of anything smaller. They do not have size in the way a grain of sand has size. They are more like points, locations where certain properties exist, such as mass, charge, and spin. They follow rules that are described not by everyday intuition, but by the mathematics of quantum mechanics. In the early universe, these particles were not arranged into anything recognizable. The universe was hot, dense, and energetic. Particles and antiparticles were constantly being created and destroyed. Energy and matter flowed into each other freely. There were no atoms, no molecules, no solid surfaces, and certainly no planets. As the universe expanded and cooled, it passed through a series of quiet transitions. Quarks began to bind together into protons and neutrons. Protons and neutrons began to form atomic nuclei. Electrons slowed down enough to be captured by those nuclei, forming the first atoms, mostly hydrogen and helium. This was one of the first moments when size began to take on a familiar meaning. An atom is not just a point. It has a structure, a tiny, dense nucleus at the centre and a cloud of electrons surrounding it. The scale of an atom is set by a balance of forces. The positive charge of the nucleus pulls the negative electrons inward. The quantum nature of the electrons prevents them from collapsing all the way in. The result is a stable, repeatable size, one that becomes the building block for everything larger. When atoms combine into molecules, size begins to grow in more interesting ways. Atoms link together through their electrons, forming bonds that create shapes. Water molecules form a bent structure. Carbon atoms can link into long chains or flat sheets, or complex three-dimensional frameworks. The specific ways atoms bond determine the properties of the material that emerges, whether it becomes a gas, a liquid, a crystal, or something flexible and organic. But even at this level, gravity is still waiting in the background. For a long time, on the scale of individual atoms and molecules, gravity is so weak that it can be ignored. The electromagnetic force dominates. Chemical bonds, electrical charges, and thermal motion decide how matter behaves. But as soon as you start to gather large amounts of matter in one place, gravity begins to matter. This is where the story of size takes a dramatic turn. Imagine a vast cloud of gas and dust drifting through space. It is made of trillions upon trillions of atoms and molecules. Each one feels a tiny gravitational pull from every other one. On its own, each pull is insignificant, but together they add up. If the cloud is large and dense enough, and if nothing disturbs it too much, the combined gravitational attraction of all those particles can begin to overcome the random motions that keep them spread out. The cloud starts to contract. As it contracts, something interesting happens. The particles fall inward, gaining speed. When they collide, they transfer that motion into heat. The cloud gets warmer. The warmer it gets, the more the particles push back against the inward pull of gravity. So again you have a familiar theme. Gravity pulling in, energy pushing out, size emerging as a balance between the two. If the cloud is massive enough, this process can continue until the centre becomes so hot and dense that nuclear fusion begins. hydrogen atoms start to fuse into helium, releasing enormous amounts of energy. A star is born. A star is, in a sense, a new level of size. It is a structure defined not just by how much matter it contains, but by what is happening in its core. The size of a star depends on its mass. A small star might be only a fraction of the sun's size, burning its fuel slowly and gently. A massive star can be dozens or even hundreds of times larger, burning brightly and living briefly on cosmic timescales. Planets emerge in the leftover material around a young star. In the swirling disk of gas and dust, tiny grains collide and stick together. Over time, these grains become pebbles, then rocks, then larger bodies called planetesimals. These in turn collide and merge, growing larger through a process called accretion. Here again, gravity takes over once the pieces become large enough. A growing planet pulls in more material, increasing its mass and its ability to pull in even more. This runaway process can lead to the formation of rocky worlds like Earth or massive gas giants like Jupiter, depending on the conditions in the disk. So from particles to atoms, from atoms to molecules, from molecules to clouds, from clouds to stars and planets, size emerges step by step. Each level is governed by a different balance of forces. Quantum rules shape atoms, chemistry shapes molecules, gravity shapes stars and planets. But this is only the beginning. Stars do not exist in isolation. They are born in groups, within large clouds that can form hundreds or thousands of stars at once. These stars move together through space, bound by their shared gravity. Over time, they can form star clusters and associations. Zoom out a little more, and you see that stars and their planets are embedded in galaxies. A galaxy is not just a random collection of stars. It is a system with structure. In spiral galaxies, stars and gas orbit the centre in a flattened disk, often with sweeping arms shaped by waves of higher density that move through the disk. In elliptical galaxies, stars move in more random three-dimensional orbits, forming rounded, featureless shapes. The size of a galaxy is determined by its mass and its history. Galaxies grow by forming new stars from gas and by merging with other galaxies. When two galaxies collide, their stars usually pass by each other without direct collisions, because the distances between stars are so vast, but their gravitational fields interact, reshaping the orbits of stars and clouds of gas. These mergers can dramatically change a galaxy's size and shape. Two spiral galaxies might merge to form a larger elliptical galaxy. A large galaxy might absorb many smaller ones over time, growing steadily through cosmic history. So size at this level is not just about accumulation, it is about transformation. Now take a step back again and consider how galaxies themselves become part of even larger systems. Galaxies gather into groups and clusters. These are held together primarily by dark matter, which forms massive invisible halos that extend far beyond the visible parts of the galaxies. The total mass of a cluster can be hundreds or thousands of times greater than that of a single large galaxy. Within a cluster, galaxies move through hot, thin gas that fills the space between them. This environment can strip gas from galaxies, slowing or stopping their ability to form new stars. Over time, this changes not just the size of the cluster, but the nature of the galaxies within it. At this point, size begins to take on a more abstract meaning. You're no longer just counting how many particles or how much mass is in one place. You're looking at how regions of the universe are connected by flows of matter and energy. Clusters are connected by filaments, which are long, thread-like regions of higher density that stretch across hundreds of millions of light years. These filaments are part of the cosmic web, the largest pattern of structure in the universe that we can currently observe. Within these filaments, galaxies and gas slowly move toward denser nodes, where clusters and superclusters form. This movement is slow, measured in hundreds of kilometers per second, which is fast by human standards, but glacial on cosmic timescales. So the emergence of size on the larger scales is less about things getting bigger in a simple way, and more about patterns becoming more pronounced. the universe began nearly uniform. Over time, gravity amplified small differences, creating a rich tapestry of dense and empty regions. Another way to think about this is in terms of energy and cooling. In the early universe, everything was hot and energetic. Particles moved quickly, resisting the pull of gravity. As the universe expanded, it cooled. Particles slowed down. This made it easier for gravity to gather matter into larger and larger structures. So size emerges not just from accumulation, but from the universe losing energy over time. This is an interesting contrast to everyday life, where we often associate growth with adding energy. A growing plant uses energy from sunlight. A growing city uses energy from fuel and electricity. On cosmic scales, growth often comes from energy being spread out, from things cooling and slowing enough to stick together. Now, consider how time fits into all of this. The universe is about 13.8 billion years old. That is a long time by any human measure, but in cosmic terms it is still a work in progress. The largest structures we see today did not form all at once. They grew gradually through countless small events. A single star forming in a cloud of gas is a small event. A galaxy absorbing a smaller neighbour is a larger one. A cluster pulling in a group of galaxies is larger still. Each step adds a layer to the final pattern. So when we ask how size emerges, one answer is that it emerges through history. Size is a record of what has happened. A massive galaxy cluster tells a story of many mergers, many flows of matter, many billions of years of gravity at work. A small, isolated galaxy tells a different story, one of relative quiet and separation. This idea becomes even more interesting when you think about the future. The universe's expansion is accelerating, driven by something we call dark energy. This means that, over time, distant regions of the universe will move away from each other faster and faster. Eventually, many galaxies and clusters will become isolated, unable to interact with anything beyond their local neighbourhood. In that far future, the emergence of size may slow or even stop on the larger scales. Gravity will still hold together what is already bound, but it will no longer be able to bring in new material from far away. So the story of size has a kind of arc. It begins with a nearly uniform universe. It grows richer and more structured over billions of years, and it may eventually settle into a more isolated, quieter state, where the larger structures are frozen in place by the expansion of space. There is also a subtle human aspect to how we think about size. We tend to imagine size as something absolute, bigger or smaller, larger or lesser. But in physics, size is often relative. A planet is large compared to a person. A star is large compared to a planet. A galaxy is large compared to a star. A filament is large compared to a galaxy. At each level, what counts as big changes. So when we talk about the largest object in the universe, we are really standing at the top of a long ladder of scale, looking down at all the smaller levels that made it possible. Without particles, there are no atoms. Without atoms, there are no clouds. Without clouds, there are no stars. Without stars, there are no galaxies. Without galaxies, there are no clusters or filaments. Everything large is built from something small, through processes that repeat, overlap and build on each other over time. As you sit with this idea, it might feel grounding to notice how it reflects your own experience. Your body is made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are made of particles. You are, in a very real sense, a structure that emerged from the same set of rules that built stars and galaxies. Different scale, same universe. Somewhere deep inside every star, far beyond the reach of any telescope or probe, a quiet and relentless process is unfolding that determines not only how bright that star will shine, but how large it will grow, how long it will live, and how it will eventually come to an end. Stars are not simply glowing spheres drifting through space. They are active systems, powered by reactions that turn mass into energy, shaping their own structure from the inside out. To understand how stars fit into the story of size in the universe, It helps to look at them not as points of light, but as engines, constantly converting the raw material of the cosmos into motion, heat, and radiation. At the heart of this process is nuclear fusion. In the core of a star, temperatures climb into the millions of degrees. At these extremes, atoms cannot remain intact in the way they do on Earth. Electrons are stripped away, leaving behind bare atomic nuclei, mostly protons in the case of hydrogen. These positively charged particles normally repel each other strongly, because like charges push apart. But in the intense pressure and heat of a stellar core, the protons are moving so fast and packed so closely together that every so often they manage to get close enough for a different force, the strong nuclear force, to take over. When that happens, they bind together. In the simplest and most common fusion process, 4 hydrogen nuclei eventually combine to form a single helium nucleus. This does not happen all at once. It proceeds through a series of intermediate steps, creating different particles along the way. The important part is the result. The helium nucleus that emerges has slightly less mass than the 4 hydrogen nuclei that went in. That missing mass does not vanish. It is converted into energy, according to Einstein's famous relationship between mass and energy. This energy is released in the form of radiation and heat. It pushes outward from the core, creating pressure that counteracts the inward pull of gravity. The balance between these two influences, gravity pulling in and energy pushing out, is what gives a star its size and stability. If gravity were acting alone, the star would collapse in on itself, becoming smaller and denser. If the energy from fusion were too strong, the star would expand and possibly tear itself apart. A stable star exists in a state known as hydrostatic equilibrium, where these two tendencies are matched closely enough that the star maintains a relatively steady size for millions or billions of years. The mass of a star plays a crucial role in how this balance works out. A small star, with less mass, has a weaker gravitational pull. It does not squeeze its core as tightly. This means the core temperature is lower, and fusion proceeds more slowly. These stars burn their fuel gently, and can shine for extremely long periods. Some of the smallest red dwarf stars in the universe are expected to live for trillions of years, far longer than the current age of the universe. A massive star, on the other hand, has a much stronger gravitational pull. It compresses its core to much higher temperatures and pressures. Fusion proceeds at a much faster rate. These stars are bright and energetic, but they burn through their fuel quickly. A star that is many times the mass of the Sun might live for only a few million years before exhausting its core hydrogen. So size and lifespan are tied together through the physics of fusion and gravity. Bigger stars live faster and die younger. Smaller stars live quietly and persistently, glowing softly across vast stretches of cosmic time. As a star ages, the nature of its nuclear engine changes. In the early part of a star's life, hydrogen fusion dominates. The star's core is filled with hydrogen, and the main task of gravity and pressure is to keep that fusion going at a steady rate. But over time, hydrogen in the core is converted into helium. Eventually the core becomes mostly helium, and the star can no longer sustain hydrogen fusion in that central region. When this happens, the balance shifts. Fusion slows down. The outward pressure decreases. Gravity begins to gain the upper hand, and the core starts to contract. As it contracts, it heats up even more. This higher temperature allows new types of fusion reactions to begin, this time involving helium nuclei. Helium fusion produces heavier elements such as carbon and oxygen, and releases additional energy. This energy pushes outward, causing the outer layers of the star to expand. The star grows larger, sometimes dramatically so. A star like the Sun will eventually swell into a red giant, becoming so large that it could engulf the inner planets of its solar system if they were still in place. In more massive stars, this process continues through a series of stages. After helium is used up, the core contracts again and heats up enough to fuse carbon, then oxygen, then silicon. Each stage produces heavier and heavier elements, all the way up to iron. This sequence of reactions builds an onion-like structure inside the star, with different layers fusing different elements at the same time. Hydrogen might still be fusing in an outer shell, while helium fuses deeper in, and heavier elements fuse closer to the core. Each of these stages affects the star's size and structure. The more advanced the fusion, the more unstable the balance between gravity and pressure can become. Iron is a special case. Fusing iron does not release energy. Instead, it absorbs it. When a massive star's core becomes mostly iron, its nuclear engine effectively shuts down. There is no longer a source of outward pressure to counteract gravity. At that point, gravity wins completely. The core collapses in a fraction of a second, compressing to extreme densities. The outer layers of the star crash down onto the collapsing core and then rebound in a violent explosion known as a supernova. For a brief time, the star can outshine an entire galaxy. This explosion does more than mark the end of a star's life. It also spreads heavy elements into space. Elements like carbon, oxygen, silicon and iron, which were forged in the star's core, are flung outward into the surrounding gas. Over time, this enriched material can become part of new clouds, new stars, and new planets. So stars are not just engines of energy. They are factories of matter. They take simple elements and build more complex ones. They distribute those elements across the galaxy, seeding future generations of stars and planetary systems. This process connects the story of stellar size to the story of cosmic structure in a deeper way. The size of a star determines how it lives and how it dies. How it dies determines what it contributes to the surrounding environment. That environment in turn influences how future stars and systems form. There's also a limit to how large a star can be. As a star's mass increases, its gravitational pull becomes stronger, which raises the core temperature and accelerates fusion. This makes the star brighter. The radiation pouring out of the star exerts a force on the outer layers, pushing them away. At very high brightness, this outward push can become so strong that it begins to blow material off the star's surface. This sets an upper bound on stellar mass. If a star becomes too massive, it cannot hold itself together. The radiation it produces will strip away its own outer layers, reducing its mass until a balance is restored. Observations suggest that the most massive stars in the universe are around a few hundred times the mass of the Sun. These stars are enormous, with diameters that can be thousands of times larger than the Sun's. They burn intensely and live very short lives, sometimes only a few million years. Their role in shaping their surroundings is outsized. Their strong radiation and powerful stellar winds carve cavities in nearby gas clouds. Their supernova explosions can trigger or suppress star formation in neighbouring regions. In this way, a single massive star can influence the structure of an entire region of a galaxy. Now consider what happens when stars gather in large numbers. A galaxy is, in part, a collection of stellar engines, all running at different speeds in different stages of life. The combined light and energy from these stars shapes the galaxy's appearance. Spiral arms glow with young, massive blue stars that burn brightly and die quickly. Older regions are dominated by redder, longer-lived stars that provide a softer, steadier light. The energy output from stars also affects the gas between them. Radiation can heat and ionize gas, preventing it from collapsing into new stars. Supernova explosions can send shock waves through the interstellar medium, compressing some regions while dispersing others. So the collective behavior of stars helps regulate how a galaxy grows and changes over time. In this sense, stars act not just as individual engines, but as parts of a larger interconnected system. When galaxies interact or merge, their stars and gas clouds respond to new gravitational forces. Gas can be funneled toward the centre, triggering bursts of star formation. Massive stars form, burn, and explode, adding energy and momentum to the system. This feedback can shape the final size and structure of the merged galaxy. On even larger scales, the light from stars becomes a tool for measurement. The combined glow of billions of stars in a galaxy can be used to estimate its mass and distance. The way that light is absorbed, scattered, or shifted provides clues about the environment between galaxies and across filaments of the cosmic web. In this way, stars connect the smaller scales of nuclear physics to the larger scales of cosmic structure. There is also an interesting relationship between stars and dark matter. Stars form from ordinary matter, but they live inside gravitational wells dominated by dark matter. A galaxy's dark matter halo determines how fast stars orbit and how gas moves. Without that invisible mass, galaxies would not hold together in the way we observe. So while stars are the visible active components, dark matter provides much of the underlying structure. The two work together to create the shapes and sizes of galaxies and clusters. Another layer of this story comes from the idea of energy flow. A star takes in mass from its surroundings during its formation. It then spends most of its life converting a small fraction of that mass into energy and radiating it into space. That energy travels outward, heating dust, illuminating gas, and eventually streaming across intergalactic space. Over cosmic timescales, this flow of energy contributes to the thermal history of the universe. Regions near active, star-forming galaxies can be warmer and more ionized than more isolated regions. This can affect how matter clumps and how structures evolve. So even though stars are small compared to galaxies or clusters, their energy output has consequences that reach far beyond their immediate surroundings. It is also worth considering how stars themselves are influenced by the larger structures. A star in a dense cluster experiences a very different environment than a star in a quiet, isolated part of a galaxy. Close encounters with other stars can alter planetary systems or even eject stars from the cluster entirely. The movement of the cluster through the galaxy can expose stars to varying levels of radiation and gas density. On even larger scales, the position of a galaxy within a cluster or along a filament can influence how much gas it receives, which in turn affects how many new stars it can form. So the cosmic web, shaped by gravity and dark matter, indirectly shapes the population of stars within it. This creates a chain of influence that runs from the largest scales to the smallest. The structure of the universe influences galaxies. Galaxies influence star formation. Stars influence their surroundings and contribute material and energy back into the system. So when we think of stars as nuclear engines of mass and energy, we can also think of them as connectors. They link the physics of the atomic nucleus to the architecture of the cosmos. There is a quiet symmetry in this. The same fundamental forces that govern the behaviour of particles inside a star's core also govern the motion of galaxies across billions of light years. The difference is not in the rules, but in the scale and in the time over which those rules play out. The largest structures in the universe are not just collections of matter. They are the cumulative result of countless smaller engines, each star contributing its own energy, its own history, and its own material to the broader pattern. Across the vast stretches of space where stars gather in their billions, there exists a kind of slow, graceful motion that is easy to miss if you only think of the universe as a collection of fixed points of light. Galaxies are not static islands. They are dynamic systems, filled with matter in motion, turning, drifting, colliding, and reshaping themselves over immense periods of time. To understand how galaxies fit into the story of the universe's larger structures, it helps to think of them not as pictures pinned to the sky, but as ongoing processes, where rotation, gravity, and the flow of material work together to create forms that can persist for billions of years. At the most basic level, a galaxy is a bound system of stars, gas, dust, and dark matter. What makes it a system rather than a random collection is that all these components share a common gravitational field. They move within it, respond to it, and help shape it. This shared field gives the galaxy its overall structure and governs how its parts behave over time. One of the most striking features of many galaxies is rotation. In spiral galaxies, like the Milky Way, stars and gas orbit the galactic centre in a flattened disk. From a distance, this can look like a giant cosmic pinwheel, with arms of light sweeping outward in slow arcs. But the motion is not as simple as a solid object spinning. Each star follows its own path, influenced by the combined gravity of all the matter in the galaxy. If you could track a single star in such a galaxy, you would find that its orbit is not a perfect circle. It moves in a slightly elongated path, gently bobbing above and below the main disk, responding to subtle variations in the gravitational pull of nearby stars, gas clouds, and the underlying dark matter halo. Over millions of years, these small influences can change the star's path, but the overall pattern of rotation remains. This rotation has deep implications for how a galaxy forms and evolves. In the early stages of a galaxy's life, matter begins to fall into a region of slightly higher density, guided by the gravitational pull of a dark matter halo. As gas and dust fall inward, they do not drop straight down into the centre. They carry a small amount of sideways motion, inherited from the random motions and tidal influences of the early universe. As the material collapses, this sideways motion becomes more important. Conservation of angular momentum, a fundamental principle of physics, means that as the radius of a rotating system decreases, its rotation speed increases. This is the same effect you see when a figure skater pulls their arms in and spins faster. So as the cloud of gas and dust contracts to form a galaxy, it begins to spin more rapidly. Over time, this rotation causes the material to flatten into a disk. Stars form within this disk, inheriting the motion of the gas from which they are born. The result is a rotating stellar system. The presence of a disk is not universal. Some galaxies, known as elliptical galaxies, do not show a clear, flattened structure. Their stars move in more random, three-dimensional orbits, creating a rounded or elongated shape rather than a thin disk. These galaxies often form through mergers, where two or more disk galaxies collide and combine. The ordered rotation of the original disks is disrupted, and the resulting system settles into a more chaotic pattern of motion. This contrast between rotating disks and more random ellipticals reveals how strongly motion and history shape a galaxy's size and form. Rotation also influences how material moves within a galaxy. In a spiral galaxy, gas clouds orbit along with the stars, but they can also drift inward or outward over time. As they move, they can be compressed by spiral density waves, which are regions of higher mass concentration that move through the disk, like traffic jams rather than like fixed structures. When gas enters one of these regions, it slows down, bunches up, and can become dense enough to form new stars. So the spiral arms you see in images are not necessarily made of the same stars all the time. They are patterns in the flow of matter, places where stars are more likely to form and where young, bright stars light up the disk. This ongoing cycle of gas flowing, compressing, forming stars, and being altered by those stars is part of what makes a galaxy a living system in a physical sense. It is not alive, of course, but it is active. Matter is constantly being rearranged, transformed, and redistributed. At the centre of many galaxies, including our own, lies a supermassive black hole. These objects can have masses millions or even billions of times greater than that of the Sun. Despite their name, they are not cosmic vacuum cleaners swallowing everything nearby. Most of the time they sit quietly, exerting their gravitational pull like any other massive object. But when gas and dust fall toward them, they can become extremely active. The infalling material forms a hot, rotating disk around the black hole, known as an accretion disk. Friction and magnetic effects within this disk cause the material to heat up and emit enormous amounts of energy. In some cases, powerful jets of particles are launched outward, extending far beyond the galaxy itself. These active galactic nuclei can influence the motion and temperature of gas across large regions of the galaxy. They can heat gas, preventing it from forming new stars. They can also push gas outward, redistributing material and altering the galaxy's structure. So even at the heart of a galaxy, rotation and motion play central roles. Now consider how galaxies interact with one another. Galaxies are not isolated. They live in groups, clusters, and along filaments of the cosmic web. As they move through these environments, they feel the gravitational pull of their neighbours and of the larger structures around them. When two galaxies approach each other, their gravitational fields begin to interact long before their visible parts touch. Stars in each galaxy feel the pull of the other, and their orbits are distorted. Gas clouds can be drawn out into long sweeping tails that extend tens or hundreds of thousands of light years into space. These interactions can trigger bursts of star formation, as gas is compressed by tidal forces. They can also disrupt the orderly rotation of disks, turning spirals into more chaotic systems. If the galaxies merge, their stars and dark matter halos combine, forming a new, larger galaxy. The resulting system often has a more complex pattern of motion, with stars moving in a wide range of orbits rather than in a simple rotating disk. Over billions of years, repeated interactions and mergers can significantly change a galaxy's size and shape. A small galaxy can be absorbed by a larger one, adding its stars and dark matter to the larger system. This process, sometimes called galactic cannibalism, is one of the main ways large galaxies grow. The Milky Way, for example, is currently in the process of absorbing several smaller satellite galaxies. Their stars are being stretched out into long streams that wrap around our galaxy, traces of past mergers written in the motion of stars. This growth through mergers is a key part of the hierarchical nature of cosmic structure. Small systems form first, they combine to form larger ones. Those larger ones combine again, building up the massive galaxies and clusters we see today. Rotation and motion are not just internal properties of galaxies, they also reflect their place in the larger cosmic environment. Galaxies within a cluster move through the cluster's gravitational field. They orbit the cluster's centre of mass, often at high speeds. As they move, they pass through the hot gas that fills the cluster. This gas can strip away a galaxy's own gas, a process known as Ram pressure stripping. When a galaxy loses its gas, its ability to form new stars is reduced or stopped. Over time, this can change a galaxy from a star-forming blue system into a quieter red one dominated by older stars. So the motion of a galaxy through its environment can directly influence its evolution. On even larger scales, galaxies tend to move along filaments of the cosmic web. These filaments act like channels, guiding the flow of matter toward dense nodes where clusters form. A galaxy's motion along a filament can determine which cluster it eventually becomes part of and what kind of interactions it experiences along the way. This means that the rotation and motion of galaxies are not just local phenomena. They are connected to the larger patterns of structure in the universe. There is also an interesting relationship between a galaxy's rotation and the presence of dark matter. When astronomers measure how fast stars and gas orbit the centre of a galaxy, they often find something unexpected. The rotation speed does not drop off with distance from the centre in the way you would expect if only the visible matter were present. Instead, the outer parts of the galaxy often rotate just as fast as the inner parts. This suggests that there is more mass in the galaxy than can be accounted for by the stars and gas alone. The most widely accepted explanation is that galaxies are embedded in massive halos of dark matter that extend far beyond the visible disk. These halos play a major role in shaping the galaxy's rotation. They provide additional gravitational pull, allowing the outer parts of the galaxy to move faster without flying apart, so the motion you see in a galaxy is, in part, a visible trace of an invisible structure. This connection between rotation and dark matter is one of the key pieces of evidence for the existence of dark matter. By studying how galaxies move, scientists infer the distribution of something they cannot see directly. Now think about what all this means for the idea of size. A galaxy's size is not just a matter of how far its stars extend. It includes the region where its dark matter halo dominates. It includes the space where its gravity influences nearby galaxies and gas. It includes the paths along which its stars and clouds move over time. So a galaxy is not just a snapshot. It is a volume of space filled with motion, history, and influence. When galaxies come together to form clusters, their individual motions combine into a larger pattern. The cluster becomes a system of systems, with galaxies orbiting within it, gas flowing through it, and dark matter shaping the overall gravitational field. At this point, the concept of rotation becomes more complex. Clusters can show signs of overall rotation, but they are often dominated by random motions. Galaxies within a cluster move in many different directions, influenced by the combined gravity of all the mass in the system. So as you move up the scale from stars to galaxies to clusters, the nature of motion changes. It becomes less orderly and more statistical. Instead of a simple rotation, you see a distribution of velocities, a kind of cosmic weather pattern of movement. And yet, even here, there is structure. There are preferred directions of motion along filaments. There are regions where matter flows inward, and others where it flows outward. All of this contributes to the larger architecture of the universe. Another way to think about galaxies as systems of matter and motion is to consider how they exchange material with their surroundings. Galaxies do not keep all their gas forever. Stellar winds, supernova explosions, and active galactic nuclei can drive gas out into intergalactic space. At the same time, galaxies can draw in fresh gas from their environment, especially along filaments. This exchange affects a galaxy's size and mass over time. A galaxy that is losing gas and not gaining much new material may stop forming stars and gradually fade. A galaxy that is drawing in gas can continue to grow and form new stars. So size is not a fixed property. It is the result of a balance between what a galaxy gains and what it loses. There is also a temporal aspect to all of this. The motion you see in a galaxy today is the result of billions of years of past interactions and flows. The paths stars follow are shaped by the gravitational field, which itself has been shaped by the galaxy's growth and mergers. So when you look at a galaxy, you are seeing a kind of memory, written in motion. At the same time, the galaxy is also shaping the future. Its gravity will influence where new stars form, how neighbouring galaxies move, and how material flows through its region of space. This interplay between past, present, and future is part of what makes galaxies such important building blocks in the universe's larger structures. From a distance, a galaxy might look like a simple, elegant shape, a spiral, an ellipse, a faint smudge of light. But up close, in terms of physics, it is a complex, evolving system where billions of objects, visible and invisible, move within a shared gravitational framework. So when we think about galaxies as rotating systems of matter and motion, we're really thinking about them as the middle layer in the universe's hierarchy of size. They sit between the small scale of stars and planets and the large scale of clusters and filaments. They translate the physics of individual engines, like stars, into the broader patterns that shape the cosmic web. Beneath everything that shines in the universe, beneath every star, every glowing cloud of gas, every bright spiral arm of a galaxy, there is something that does not announce itself with light at all, yet quietly outweighs and outshapes almost everything we can see. Dark matter is not a single object you can point to, or a substance you can hold in a container. It is a presence inferred from motion, from gravity, and from the way the visible universe behaves when something unseen is clearly pulling the strings. The idea of dark matter did not begin as a bold theory about invisible particles drifting through space. It began as a practical problem. When astronomers started carefully measuring how galaxies rotate, they noticed something that did not fit the simple expectations of gravity. If you take a galaxy and assume that most of its mass is in the stars and gas you can see, you can calculate how fast those stars should orbit the centre. Stars close to the centre should move quickly, because they feel a strong gravitational pull from all the mass inside their orbit. Stars farther out should move more slowly because there is less mass inside their orbit pulling on them. That is how the solar system works. Planets close to the Sun move quickly. Planets far away move more slowly. But when astronomers measured the rotation of galaxies, they found a surprise. The stars far from the centre were not slowing down. They were moving just as fast as the stars much closer in. In some cases, they were even moving faster. This meant that there had to be more mass in the galaxy than what was visible. Otherwise, the outer stars should have been flung off into space, unable to stay in orbit around the galaxy's centre. So scientists concluded that galaxies must be embedded in large halos of unseen matter, extending far beyond the bright disks and bulges that telescopes can detect. This unseen matter provided the extra gravitational pull needed to keep the outer stars moving at the speeds observed. At first, this was a radical idea. The notion that most of the mass in the universe could be invisible challenged centuries of thinking, where matter and light were closely linked. If something had mass, it usually interacted with light in some way. It glowed, reflected, absorbed, or scattered it. Dark matter, by definition, does none of these things, at least not in any way we can currently measure. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter without noticeable interaction, except through gravity. So how do we know it is there at all? One of the most powerful tools for detecting dark matter is gravitational lensing. According to Einstein's theory of general relativity, mass bends space-time. Light travelling through curved space-time follows a curved path. So if there is a large concentration of mass between us and a distant galaxy, the light from that galaxy can be bent, distorted, or even split into multiple images. By studying how background galaxies are distorted across the sky, astronomers can map the distribution of mass in the foreground, whether that mass is visible or not. When they do this, they find that the mass inferred from lensing often far exceeds the mass of the visible stars and gas. The extra mass lines up with the locations of galaxies and clusters, but it also extends far beyond them, forming large, smooth halos and filaments. This is one of the clearest pieces of evidence that dark matter is real and widespread. Another clue comes from galaxy clusters. Clusters are the largest structures in the universe that are clearly held together by gravity. They contain hundreds or thousands of galaxies, along with vast amounts of hot gas that glows in X-rays. If you add up the mass of all the stars in the galaxies and all the hot gas in the cluster, you still fall far short of the amount of mass needed to keep the cluster gravitationally bound. Without extra mass, the galaxies would be moving too fast to stay together. The cluster would fly apart. Once again, dark matter fills the gap. In fact, in most clusters, dark matter makes up about 80 to 90% of the total mass. The glowing part of the universe, everything you can see with telescopes, is only a small fraction of what is actually there. So when we talk about the largest structures in the universe, we are mostly talking about structures made of dark matter. The visible galaxies and gas are like a thin layer of frost on a much larger invisible framework. This is why dark matter is often described as scaffolding. In the early universe, long before stars and galaxies formed, dark matter began to clump together under the influence of gravity. Ordinary matter, which was still hot and strongly interacting with radiation, could not collapse as easily. It was pushed around by light and pressure. Dark matter, on the other hand, did not care about radiation. It could respond only to gravity. So it began to form dense regions and filaments first. As the universe cooled, ordinary matter fell into these dark matter structures. Gas flowed along the filaments and collected in the densest regions, where it eventually formed stars and galaxies. So the large-scale pattern of the universe, the cosmic web of filaments and nodes, was shaped primarily by dark matter. The galaxies we see today are, in a sense, lighting up this hidden structure. This is why, when astronomers map the distribution of galaxies across the sky, they find a pattern that matches the distribution of dark matter inferred from lensing and simulations. The visible universe traces the shape of the invisible one. Understanding this scaffolding is essential for understanding size on cosmic scales. Without dark matter, gravity alone, acting on ordinary matter, would not be able to build the larger structures we see today in the time available since the Big Bang. Galaxies would form more slowly. Clusters might not form at all. The cosmic web would be much less pronounced. So dark matter is not just an extra ingredient, it is the main framework that allows gravity to do its work efficiently on large scales. Now, what exactly is dark matter? This is one of the biggest open questions in modern physics. We know what dark matter is not. It is not made of ordinary atoms. If it were, it would interact with light in ways we could detect. It would absorb or emit radiation. It would show up in spectra. It would glow faintly in the cold of space. It also cannot be made of black holes or other massive compact objects in large enough numbers to account for all the dark matter. Those would produce gravitational effects such as micro-lensing events that we would see much more frequently than we do. So most scientists think dark matter is made of some kind of new particle, one that does not interact strongly with ordinary matter or with light, but does have mass and therefore gravity. There are many candidates. Some theories propose weakly interacting massive particles, often called WIMPs. Others suggest lighter particles, such as axions. There are even more exotic ideas, involving hidden sectors of physics that barely interact with the particles we know. Despite decades of experiments, no one has yet directly detected a dark matter particle in a laboratory. Underground detectors, space-based observatories, and particle accelerators have all searched for signs of dark matter interacting with ordinary matter, but so far the evidence remains indirect. This means that much of what we know about dark matter comes from its gravitational effects on visible structures. This is where the connection to the largest objects in the universe becomes especially strong. When scientists simulate the growth of the universe on a computer, they start with the conditions measured in the cosmic microwave background, the faint radiation left over from the early universe. They include dark matter as a major component and let gravity and expansion shape the distribution of matter over billions of years. The result of these simulations is a cosmic web that looks remarkably similar to what we observe. Filaments form, clusters appear at the intersections, voids open up in between. If you run the same simulation without dark matter, the result looks very different. Structure forms much more slowly and on much smaller scales. The large coherent patterns we see in galaxy surveys do not appear. So dark matter is not just a detail, it is a defining feature of the universe's largest structures. There is also an important distinction between dark matter and dark energy, which are sometimes confused because of their names. Dark matter is something that clumps. It gathers under gravity. It helps build structures. Dark energy, on the other hand, is something that appears to drive the expansion of the universe. It does not clump in the same way. It is more like a property of space itself, pushing regions of space apart over time. So in the cosmic story, dark matter is the builder, while dark energy is the force that eventually limits how far the builder's influence can reach. This interplay shapes the ultimate size of the largest structures. In the early universe, dark matter dominated. Gravity pulled matter together, and structures grew rapidly. As the universe aged, dark energy became more important. The expansion of space began to accelerate. This makes it harder for gravity to pull distant regions together. So there is a kind of window of time during which the largest structures can form. Before that, the universe was too hot and uniform. After that, the expansion becomes too strong. The largest filaments and superclusters we see today may represent the peak of this process, the moment when gravity and dark matter had enough time to build enormous patterns, but before dark energy fully took over. Now think about how this invisible scaffolding affects what we actually see. A galaxy does not sit at the centre of its dark matter halo like a bead on a string. It moves within it. Stars orbit within the combined gravitational field of the visible matter and the dark matter. When galaxies interact, it is often their dark matter halos that interact first. The halos can overlap and merge, pulling the visible galaxies together. So even when you see two galaxies colliding in a dramatic image, what you are really seeing is the luminous surface of a much larger invisible interaction between their dark matter structures. On the scale of clusters, the same thing happens. When two clusters collide, the dark matter halos pass through each other relatively smoothly, because dark matter does not interact strongly with itself or with ordinary matter. The hot gas, on the other hand, can collide and slow down, creating shock fronts and bright X-ray features. By studying these kinds of collisions, astronomers can separate the distribution of dark matter from the distribution of ordinary matter, providing some of the clearest evidence that dark matter is a distinct component of the universe. All of this leads to a subtle but important shift in how we think about size. The largest objects in the universe, in terms of mass and influence, are not the things we can see. They are vast, invisible structures made mostly of dark matter, stretching across hundreds of millions or billions of light years. The galaxies and clusters we observe are like markers, highlighting the shape of something much larger and more diffuse. So when someone points to a great wall of galaxies and calls it the largest object ever found, what they are really pointing to is a luminous outline of an even larger dark matter structure. This also means that our maps of the universe are, in a sense, incomplete. We see only the parts that shine. The rest we infer through careful measurements and models. There is something quietly humbling about this. Most of what shapes the universe's largest patterns is something we cannot see directly and do not yet fully understand. Another interesting aspect of dark matter's role as scaffolding is how it influences the stability of structures. Because dark matter halos are large and extended, they provide a kind of gravitational cushion. They can absorb and redistribute energy during mergers and interactions. This can help keep galaxies and clusters bound together even after violent events. In this way, dark matter contributes to the persistence of large structures over time. Without it, the universe might be a much more chaotic place, with fewer long-lived systems. It also affects how far a structure's influence extends. A galaxy's dark matter halo can reach far beyond its visible stars. This means that a galaxy can gravitationally influence other galaxies at distances much greater than you might expect from looking at the light alone. On the scale of filaments, overlapping halos and the collective mass of dark matter shape the paths along which matter flows. So the invisible scaffolding is not just a background, it is an active participant in the dynamics of the universe. There is still much we do not know. We do not know what dark matter is made of. We do not know how it behaves on the smallest scales. There are hints that it might not be perfectly smooth, that it could have its own kind of structure, forming small clumps within larger halos. If that is true, it could influence how the smallest galaxies form and how stars are distributed within them. So even as we talk about the largest objects in the universe, there is an ongoing investigation into the smallest building blocks of the invisible matter that makes those objects possible. This creates an interesting symmetry. At one end of the scale, physicists are building sensitive detectors deep underground, trying to catch a single dark matter particle interacting with ordinary matter. At the other end of the scale, astronomers are mapping billions of galaxies across the sky, tracing the shape of the cosmic web. Both efforts are part of the same quest, to understand the hidden framework that gives the universe its shape. The universe is having two layers, one that shines and one that does not, one that announces itself with light and colour, and one that works quietly in the background, guiding motion and growth without ever stepping into the spotlight. Far beyond the scale of individual galaxies, in regions where the universe's invisible framework dips into some of its deepest contours, enormous gatherings of matter take shape that can best be understood as valleys in a vast gravitational landscape. These are galaxy clusters, and they are not just collections of galaxies drifting near each other by chance. They are massive structured systems where gravity has carved out a well so deep that it draws in light, gas, and entire galaxies, holding them together across millions of light years and billions of years of time. To picture what a cluster is, it can help to imagine the universe as an ocean of space and matter, gently expanding in all directions. In most places, this ocean is relatively smooth, but here and there the surface dips. These dips are caused by concentrations of mass, mostly dark matter, that bend space-time and create regions where motion naturally flows inward. A galaxy cluster is one of the deepest of these dips, a place where matter has gathered in such large quantities that its gravitational pull dominates its surroundings. At first glance, a cluster might look like a loose swarm of galaxies scattered across the sky. But this apparent looseness hides a powerful underlying order. The galaxies within a cluster are not free to wander wherever they like. They move within a shared gravitational field, orbiting a common centre of mass, much like planets orbit a star, though on a far grander and slower scale. The distances involved are immense. A typical large cluster can span several million light-years from one side to the other. Even so, gravity is strong enough within this region to keep hundreds or thousands of galaxies bound together, resisting the overall expansion of the universe. The visible galaxies, however, are only part of the story. Between the galaxies and a cluster lies a vast amount of hot, thin gas known as the intracluster medium. This gas is heated to temperatures of tens of millions of degrees as it falls into the cluster's gravitational well. At these temperatures, it emits X-rays, which can be detected by space-based telescopes. In many clusters, the mass of this hot gas rivals or even exceeds the total mass of all the stars in the galaxies combined. And yet, even this gas is not the dominant component. Most of a cluster's mass is in dark matter. The dark matter forms a massive extended halo that defines the shape and depth of the gravitational well. The galaxies and the hot gas are embedded within this halo, moving under its influence. So when you look at a cluster, what you are really seeing is the luminous surface of a much larger invisible structure. Understanding clusters as gravitational wells helps explain many of their properties. For example, galaxies within a cluster often move at very high speeds, sometimes thousands of kilometers per second. These speeds are not random. They reflect how deep the gravitational well is. The deeper the well, the faster objects can move within it without escaping. By measuring the velocities of galaxies in a cluster, astronomers can estimate the total mass of the cluster. They compare the observed speeds to what gravity would predict for a given amount of mass. Time and again, the result is the same. There is far more mass present than can be accounted for by the visible matter alone. The hot gas provides another way to probe the cluster's gravitational field. The gas is held in place by gravity, balanced against the pressure created by its high temperature. By studying how the temperature and density of the gas change with distance from the cluster's centre, scientists can infer the shape of the gravitational well. Gravitational lensing adds yet another layer of information. Light from background galaxies is bent as it passes through the cluster's mass. By mapping these distortions, astronomers can create detailed maps of the cluster's total mass distribution, including both visible and dark matter. All these methods converge on the same picture. A galaxy cluster is a massive, extended structure dominated by dark matter, with galaxies and gas tracing out the shape of a deep gravitational basin. Now, consider how such a structure comes into being. Clusters do not form all at once. They grow over time through a process of accretion and merging. In the cosmic web, filaments of dark matter and gas connect clusters to their surroundings. Along these filaments, smaller groups of galaxies and individual galaxies flow inward, guided by the gravitational pull of the cluster. When a group of galaxies approaches a cluster, it does not simply fall straight in and stop. It enters the cluster's gravitational field, picks up speed, and begins to orbit. Over time, interactions with other galaxies, with the hot gas, and with the cluster's overall gravitational field can strip away gas and alter the group structure. Eventually, the group becomes part of the cluster, its identity absorbed into the larger system. This process can be dramatic. When two large clusters collide, the event is one of the most energetic in the universe since the Big Bang. The galaxies themselves, because of the vast distances between stars, usually pass by each other without direct collisions. The dark matter halos, which also interact primarily through gravity, pass through each other relatively smoothly. The hot gas, however, does collide. It slams together, slows down, and heats up even more, creating shock waves that can be seen in X-ray images. These collisions can temporarily reshape the cluster, creating complex asymmetric structures. One famous example is known as the bullet cluster. In this system, two clusters have passed through each other. The hot gas from each cluster has collided and slowed down, while the dark matter halos and galaxies have moved ahead. This separation between visible matter and mass, revealed through gravitational lensing, provides strong evidence that dark matter is a distinct component that behaves differently from ordinary matter. Events like this highlight the role of clusters as dynamic, evolving systems, not static piles of galaxies. Within a cluster, the environment is very different from that of a quiet, isolated galaxy. The hot intracluster gas exerts pressure on galaxies moving through it. This pressure can strip away a galaxy's own gas, especially from its outer regions. Without gas, the galaxy cannot form new stars. Over time, this can transform a galaxy from a star-forming blue system into a red, quiescent one dominated by older stars. This means that the cluster's gravitational well does more than hold galaxies in place. It actively influences their internal evolution. Close encounters between galaxies are also more common in clusters. The high density of galaxies increases the chances of gravitational interactions. These interactions can distort galaxy shapes, trigger bursts of star formation, or even lead to mergers. So a cluster is not just a container for galaxies, it is an environment that shapes what those galaxies become. Another important feature of clusters is that they often have a central, dominant galaxy, sometimes called a brightest cluster galaxy. These galaxies can be enormous, far larger than typical galaxies like the Milky Way. They often sit near the bottom of the cluster's gravitational well, where matter tends to accumulate. These central galaxies grow by merging with smaller galaxies that sink toward the centre over time, a process driven by gravitational interactions that gradually remove energy from their orbits. The presence of such a massive central galaxy is another sign of how clusters act as gathering points for matter. Now let's think about clusters in the context of the larger structures in the universe. Clusters are the nodes of the cosmic web. They sit at the intersections of filaments, where matter flows in from multiple directions. If you were to draw a map of the universe's large-scale structure, clusters would appear as bright points connected by long, faint lines. These connections mean that clusters are not isolated. They are part of a larger network. However, there is an important distinction to make. While the galaxies within a cluster are generally gravitationally bound to each other, the same is not always true for clusters within a supercluster. A supercluster is a large region containing multiple clusters and groups of galaxies. Some parts of a supercluster may be bound together, while others are slowly drifting apart due to the expansion of the universe. So clusters represent a kind of upper limit to gravitational binding. They are among the larger systems in which gravity can still fully overcome cosmic expansion and keep everything together over long periods of time. This makes clusters especially interesting when thinking about the largest possible objects. They are massive, they are extended, they are clearly defined as systems with a shared gravitational future. Beyond clusters, structures become looser, more transient, and more dependent on how you choose to define them. Another way to understand clusters as gravitational wells is to consider their effect on time and light. According to general relativity, a deep gravitational well can slow down time slightly. Clocks in a strong gravitational field tick more slowly than clocks far away. The effect is tiny on human scales, but in the deep wells of galaxy clusters, it becomes measurable. Light climbing out of a gravitational well also loses a small amount of energy, becoming slightly redshifted. This gravitational redshift can be detected in the light from galaxies and gas in clusters, providing yet another way to probe the depth of the well. So clusters do not just shape the motion of matter, they also subtly influence the flow of time and the properties of light within their domain. There is also a connection between clusters and the history of the universe. Because clusters take a long time to form, their abundance and distribution across the sky provide clues about the conditions of the early universe and the nature of dark matter and dark energy. If the universe had slightly different initial density fluctuations, or if dark matter behaved differently, the number and size of clusters today would be different. By counting clusters at different distances, which correspond to different times in the past, astronomers can track how structure has grown over cosmic history. This makes clusters powerful tools for testing cosmological models. Now, consider the scale of energy involved. The gravitational binding energy of a large cluster is enormous. It represents the energy that would be required to pull all the cluster's components apart and scatter them into space. This energy is stored in the motion of galaxies, in the heat of the intracluster gas, and in the deep curvature of space-time created by the cluster's mass. In a sense, a cluster is a reservoir of gravitational energy, slowly converting that energy into heat, radiation, and motion as matter falls in and interacts. This continuous conversion is part of what makes clusters such active regions, even though on human timescales they appear quiet and unchanging. Another subtle aspect of clusters as gravitational wells is how they influence the flow of matter beyond their immediate boundaries. A cluster's gravitational pull can extend far into the surrounding filaments, affecting the motion of galaxies and gas tens of millions of light-years away. This creates a region of influence that is larger than the cluster's core and visible extent. In this way, clusters help shape the larger-scale patterns of the cosmic web. They act as anchors, defining where filaments converge and where voids open up. So even though clusters are not the largest structures in the universe in terms of sheer length, they play an outsized role in organising the universe's architecture. There is also an interesting relationship between clusters and the future of cosmic structure. As dark energy continues to drive the expansion of the universe, regions of space that are not gravitationally bound will move farther and farther apart. Over very long timescales, clusters will become isolated islands in an ever-expanding cosmic sea. Galaxies and clusters that are not already bound to each other will eventually slip beyond each other's reach, their light stretched and faded by the expansion. In that distant future, clusters may represent the largest coherent structures that still exist, the last places where matter remains gathered together in meaningful systems. This gives clusters a kind of long-term significance. They're not just products of the universe's past. They may also be the enduring features of its far future. Another perspective on clusters comes from thinking about them as laboratories. Because clusters contain large amounts of dark matter, hot gas, and galaxies in a single system, they allow scientists to study how these components interact under extreme conditions. The physics of the intracluster gas involves high-energy processes, magnetic fields, and shock waves. The motion of galaxies reveals information about gravity and dark matter. The distribution of mass provides tests for theories of cosmology. So clusters are not just large, they are informative. They are places where many of the universe's fundamental processes come together in a single, observable structure. As you sit with this idea, it can be helpful to imagine a cluster not as a distant, abstract concept, but as a region of space where countless individual histories overlap. Each galaxy in the cluster has its own past, its own stars, its own planets, its own internal dynamics. All of those stories are now woven together by a shared gravitational field. The cluster itself has a history, built from mergers, accretion, and the slow flow of matter along filaments. It has a present, defined by the motion of its galaxies and the glow of its hot gas. And it has a future, shaped by the balance between gravity and the expansion of the universe. So when we talk about clusters as gravitational wells in the cosmic sea, we're talking about more than just size. We're talking about places where the universe's structure becomes especially deep, layered and interconnected. Between the deep gravitational basins where clusters gather and the broad, open regions where matter is scarce, the universe reveals a structure that is less like a scattered collection of islands and more like a network, stretched across space in long, delicate threads. These threads are the filaments of the cosmic web, and the wide, quiet spaces between them are the voids. Together they form the largest pattern of organisation we can currently observe, a pattern shaped by physics that operates patiently, almost imperceptibly, over the full age of the universe. To understand why the universe looks this way, it helps to return once more to its earliest moments. After the Big Bang, matter was spread out nearly evenly. The universe was hot, dense, and filled with a mixture of particles, radiation, and dark matter. But embedded in this near uniformity were tiny variations in density. Some regions had just a little more matter than average. Others had just a little less. These small differences were the seeds of everything that followed. As the universe expanded and cooled, gravity began to amplify those differences. Regions that were slightly denser exerted a slightly stronger gravitational pull. Over time, they drew in more matter, becoming denser still. Regions that were slightly less dense lost matter to their neighbours and became emptier. This simple process, repeated across the vast expanse of space and over billions of years, gradually transformed a nearly smooth universe into one filled with structure. Dark matter played a leading role in this transformation. Because it does not interact with light or radiation, it was able to begin clumping under gravity earlier than ordinary matter. It formed a kind of invisible network of dense regions and connecting strands. Later, as ordinary matter cooled and decoupled from radiation, it fell into this network, flowing along the same paths and collecting in the same places. So the cosmic web we see today is, at its core, a map of where dark matter has gathered, with visible galaxies tracing its shape. Filaments are the highways of this web. They are long, narrow regions where matter density is higher than average, stretching across tens or hundreds of millions of light years. Along these filaments, galaxies, gas and dark matter are more concentrated, and motion tends to be directed toward the densest nodes, where clusters and superclusters reside. If you could view the universe from far enough away, the filaments would appear as faint, glowing lines connecting bright points, like a three-dimensional spider's web made of light and shadow. Voids, by contrast, are the open spaces between these threads. They are enormous regions of space with very few galaxies, sometimes spanning tens of millions of light years in diameter. They are not completely empty. There is still dark matter and thin gas within them, but the density is much lower than in the filaments and nodes. These voids are not passive gaps. They are dynamic regions shaped by the same forces that create filaments. As matter flows out of less dense regions and into denser ones, voids expand. Over time they become larger and more empty, pushing the filaments and clusters around them farther apart. So the cosmic web is not static. It is a living pattern, constantly being reshaped by the flow of matter and the expansion of space. One way to think about this is to imagine the universe as a vast landscape of hills and valleys, where gravity causes matter to roll downhill. The valleys are the clusters and dense filaments. The hills are the voids. Over time, matter rolls away from the hills and into the valleys, making the valleys deeper and the hills higher. But unlike a static landscape on Earth, this cosmic landscape is itself stretching. The ground is being pulled apart even as matter is rolling across it. This interplay between gravity and expansion gives the cosmic web its characteristic form. On smaller scales, gravity dominates. Matter falls into filaments and clusters. On larger scales, expansion becomes more important, pulling regions of space away from each other and limiting how far gravity's influence can reach. The result is a pattern that has a kind of natural size scale. Filaments and voids grow over time, but they do not merge into a single, all-encompassing structure. Instead, the universe remains a network of connected regions separated by expanding gaps. Now, consider what a filament actually contains. Along a filament you find galaxies, groups of galaxies, gas, and a significant amount of dark matter. The dark matter forms the backbone of the filament, creating a gravitational channel that guides the motion of everything else. Galaxies within a filament tend to have their own motions, but there is often a subtle overall flow along the length of the filament, directed toward the nearest cluster or dense node. Over billions of years, this flow can deliver large amounts of matter into clusters, helping them grow. The gas within filaments is usually much cooler and thinner than the gas inside clusters, but it still plays an important role. It can be a reservoir of material that galaxies draw on to form new stars. It can also be heated and ionized by the radiation from galaxies and quasars, changing its properties over time. Detecting this filament gas is challenging because it is faint and diffuse. But observations using sensitive instruments and clever techniques, such as looking for the absorption of background light, have begun to reveal it, confirming that filaments are not just chains of galaxies, but extended structures filled with matter. Voids, meanwhile, have their own subtle physics. Within a void, the gravitational pull from surrounding filaments and clusters is relatively weak. Matter has mostly flowed out, leaving behind a region where expansion dominates. Galaxies that do exist in voids tend to be small and isolated, with fewer interactions and mergers. These galaxies often have a different character from those in dense environments. They may continue forming stars for longer periods because they are not stripped of gas by hot cluster environments or frequent encounters. So the cosmic web does not just shape where galaxies are, it shapes what they become. There is also an interesting geometric aspect to filaments and voids. When scientists analyse large surveys of galaxies, they find that the cosmic web has a characteristic pattern of connectivity. Filaments often intersect at roughly 3 or 4 directions, creating nodes where clusters form. Voids tend to be surrounded by a network of filaments, like bubbles in a foam. This resemblance to a foam or a sponge is more than just a visual analogy. It reflects the way matter flows and accumulates under gravity in an expanding space. Regions of a low density expand, pushing matter into the walls between them. Those walls become filaments and sheets. Where walls intersect, nodes form. This process can be modelled mathematically, and simulations of cosmic structure formation often produce patterns that look strikingly similar to what is observed in galaxy surveys. The physics behind this involves not just gravity, but also the initial conditions of the universe and the properties of dark matter. The tiny density variations present in the early universe had a certain statistical pattern, often described in terms of a power spectrum. This pattern determines how much structure exists on different size scales. Some scales have more variation than others, leading to preferred sizes for filaments and voids. Dark matter's behaviour also matters. If dark matter particles move quickly, they can smooth out small-scale variations, preventing the formation of very small structures. If they move slowly, they allow structure to form on smaller scales. So by studying the sizes and shapes of filaments and voids, scientists can learn about the properties of dark matter and the conditions of the early universe. Another layer of complexity comes from the fact that the cosmic web is three-dimensional, but we often see it projected onto the two-dimensional surface of the sky. When astronomers map galaxies, they measure not just their positions on the sky, but also their distances, using techniques based on redshift and brightness. This allows them to build three-dimensional maps of the universe. In these maps, filaments appear as extended structures in space, not just lines on the sky. Voids appear as large, roughly spherical or elongated regions with few galaxies inside. These maps reveal that the universe is structured on scales of hundreds of millions of light-years. with a repeating pattern of dense and empty regions. However, defining the exact boundaries of a filament or a void is not always straightforward. Unlike a solid object, a filament does not have a sharp edge. Its density gradually decreases as you move away from its centre. At some point, it blends into the surrounding void. So scientists often define filaments and voids based on thresholds. They might say that a filament is a region where the density of matter is above a certain value, and a void is a region where it is below another value. These definitions can vary depending on the method used and the data available. As a result, different studies might identify slightly different structures in the same region of space. This brings us back to the idea that the largest structures in the universe are, in part, defined by how we choose to look at them. Another interesting aspect of the cosmic web is how it evolves over time. In the early universe, filaments were shorter and less pronounced. Voids were smaller and less empty. As time passed, gravity drew more matter into the filaments and clusters, making them denser. Voids expanded and became emptier. So the contrast between dense and empty regions increased over cosmic history. This process is still ongoing, but it is being slowed and altered by dark energy. As the expansion of the universe accelerates, it becomes harder for matter to flow into filaments and clusters from very far away. Over time, the growth of large-scale structure will slow and eventually stop. In the distant future, the cosmic web may become a more frozen pattern, with clusters and filaments isolated from each other by vast, expanding voids. There is also a connection between the cosmic web and the distribution of temperature and radiation in the universe. Regions of high density, like clusters and filaments, can heat the surrounding gas through shocks and radiation from stars and active galactic nuclei. This can create a warm-hot intergalactic medium that fills the filaments and the edges of voids. This warm-hot gas is difficult to detect, but it may contain a significant fraction of the universe's ordinary matter. So filaments and voids are not just features of dark matter and galaxies. They are also reservoirs of baryonic matter that we are still learning to observe and understand. Another point worth considering is how the cosmic web connects to the idea of the largest object. If you take a single filament, it can be hundreds of millions of light-years long. If you take a network of connected filaments and nodes, you can trace a structure that spans billions of light-years. But because the web is continuous and interconnected, it becomes difficult to draw a boundary and say where one structure ends and another begins. Is a great wall of galaxies a single object? Or is it just a particularly prominent section of the cosmic web? Is a supercluster a distinct system, or is it part of a larger, more diffuse pattern? These questions do not always have clear, objective answers. They depend on definitions, thresholds, and the level of detail in the data. From a physical perspective, one useful distinction is whether a structure is gravitationally bound. Filaments and voids, on the larger scales, are not fully bound systems. Their parts may be connected by a pattern of density, but they are not all destined to remain together over cosmic time. Expansion will eventually pull many of them apart. Clusters, as we discussed earlier, are more clearly bound. They represent regions where gravity has overcome expansion. So the cosmic web sits in an intermediate category. It is a pattern of connection rather than a single, unified object. Another way to think about it is in terms of flow. Matter flows along filaments into clusters. It flows out of voids into filaments. This flow gives the web a kind of directionality, even though the universe, on the larger scales, is expanding in all directions. These flows can be measured by observing the motions of galaxies and the distortions in the cosmic microwave background caused by moving clusters. By studying these flows, scientists can test theories of gravity and expansion and look for signs of new physics. So filaments and voids are not just passive features, they are active parts of the universe's dynamical system. There is also a philosophical angle to all of this. When you look at an image of the cosmic web, with its delicate threads and vast empty spaces, it can evoke a sense of structure and order on a scale that is hard to reconcile with everyday experience. But this order is not imposed from outside. It emerges naturally from simple rules: gravity, expansion, and the properties of matter. From tiny fluctuations in the early universe, a vast interconnected network has grown, linking galaxies across billions of light years. So when we talk about the largest patterns in the universe, we are really talking about the long-term outcome of very small beginnings, amplified by time and the persistent pull of gravity. At a certain point in this outward journey through scale and structure, the question quietly changes. Instead of asking how large something can be, it becomes more precise, more physical. How large can something be and still hold itself together? In a universe where space itself is stretching, where distant regions are being carried away from one another by expansion, gravity does not have unlimited reach. There is a threshold beyond which even the combined mass of countless galaxies cannot pull a structure into a shared future. So when physicists talk about the largest structures bound by gravity, they are really talking about the outer limits of what can still be called a single coherent system. To understand this limit, it helps to picture the universe as a kind of flowing field rather than a static stage. Everywhere, space is expanding. On small scales, like within a solar system or a galaxy, this expansion is completely overwhelmed by gravity. The gravitational pull between nearby masses is strong enough to hold everything together without any noticeable effect from the stretching of space. On very large scales, however, expansion becomes dominant. The farther apart two regions are, the faster the space between them grows. At some point, the pull of gravity becomes too weak to overcome this outward motion. When that happens, those regions are no longer part of the same gravitational system. They're carried away from each other, destined to become permanently isolated. So the largest gravitationally bound structures sit right at this boundary where gravity and expansion are in a kind of long-term balance. One of the most important concepts here is the idea of a gravitationally bound system. This is a collection of matter whose total gravitational pull is strong enough that its parts will continue to interact with each other indefinitely. Rather than being pulled apart by the expansion of the universe, a galaxy is clearly bound. The stars within it orbit a shared centre, and will continue to do so for billions of years. A galaxy cluster is also bound. The galaxies within it move at high speeds, but the cluster's deep gravitational well keeps them from escaping. Beyond that, things become less clear. Superclusters, which are large regions containing multiple galaxy clusters and groups, often appear as impressive, coherent structures on maps of the universe. They can span hundreds of millions of light years and contain the mass of tens of thousands of galaxies. But when scientists look carefully at the motions of galaxies within superclusters, they find that not all of them are moving in a way that suggests a shared gravitational destiny. Some regions within a supercluster are falling toward a common centre, but other regions are moving away, carried outward by the expansion of space. This means that a supercluster is not always a single bound object. It can be a mixture of bound and unbound parts, a transitional structure that looks unified in a snapshot of the universe, but does not remain unified over long periods of time. So where, then, is the true upper limit of gravitational binding? One useful way to define this limit is through the concept of a turnaround radius. This is the distance from the centre of a massive structure, where the inward pull of gravity exactly balances the outward push of cosmic expansion. Inside this radius, matter is falling inward or orbiting within the system. Outside this radius, matter is moving away, carried by the expansion of space. For a galaxy cluster, the turnaround radius can be several times larger than the visible extent of the cluster. It marks the boundary of the region that is truly part of the cluster's gravitational domain. Within this region, the future is shared. Galaxies may merge, gas may fall in, and the system may evolve, but it will remain a system. Beyond this region, the future is separate. Objects may look close now, but over billions of years they will drift farther and farther away, their connection fading. So when scientists talk about the largest structures bound by gravity, they often mean the largest systems that have a well-defined turnaround radius. In today's universe, the biggest of these are massive galaxy clusters, and in some cases tightly bound groups of clusters that are in the process of merging. One particularly well-studied example is the Laniakea region, which includes the Milky Way and many nearby galaxy clusters. Within this region, scientists have identified a large-scale flow of galaxies moving toward a common gravitational basin known as the Great Attractor. This flow suggests that at least part of this region is gravitationally connected, sharing a general motion toward a deeper potential well. However, even in this case, not all of Laniakea is expected to remain bound forever. Some parts of it may eventually be pulled away by the accelerating expansion of the universe. So the true long-term bound core may be smaller than the region we currently map as a supercluster. Another way to approach this question is through energy. In physics, a system is bound if the total energy of its components is negative. This means that the energy required to pull the system apart is greater than the energy the system currently has. The components do not have enough motion to escape each other's gravitational pull. For a galaxy cluster, this is often the case. The combined mass of the cluster creates a gravitational potential deep enough that the galaxies and gas within it do not have sufficient kinetic energy to leave. For larger structures, like superclusters or great walls, the total energy can be closer to zero or even positive in some regions. This means that some parts of the structure may eventually escape, even if they are currently connected in a loose pattern. So the largest bound structures are not necessarily the longest or the most visually impressive. They are the ones where gravity has truly won over expansion. Now, consider what sets the scale of these structures. The answer lies in a combination of the universe's age, the amount and distribution of matter, and the rate of expansion. Gravity has had about 13.8 billion years to work. Over that time, it has pulled matter together into increasingly large systems. But it has been working against an expanding background, and more recently, against an expansion that is accelerating due to dark energy. So there is a window of opportunity for structure formation. Early on, the universe was too hot and smooth for large structures to form. Later, dark energy began to dominate, slowing the growth of new large-scale structures. The result is that the largest bound structures we see today may represent the peak of what gravity can build in this particular universe. If the universe were older, or if dark energy were weaker, gravity might have had time to build even larger bound systems. If dark energy were stronger, or if the universe were younger, even clusters might not have formed. So the size of the largest bound structures is, in a sense, a reflection of the universe's overall properties. There is also a connection to the distribution of dark matter. Clusters form at the densest nodes of the dark matter network. These nodes represent the deepest gravitational wells. The mass of dark matter in these regions determines how large and how deep the well can become. The largest clusters can have total masses of more than 1,000,000,000 times the mass of the Sun. Their gravitational influence can extend tens of millions of light-years into surrounding space. These are among the most massive bound objects in the universe. In some cases, 2 or more clusters can be in the process of merging. During this process, they may form a temporary bound system that is even larger and more massive than either cluster alone. However, these mergers take billions of years to complete, and the outcome depends on the balance between gravity and expansion. Some merging systems may fully combine into a single larger cluster. Others may only partially merge before the expansion of space pulls them apart again. This highlights the dynamic nature of the boundary between bound and unbound structures. Another interesting aspect of the largest bound systems is how they affect their surroundings. A massive cluster can influence the motion of galaxies and groups far beyond its core. Its gravitational pull can create large-scale flows of matter, drawing in material along filaments. These flows can shape the structure of the surrounding cosmic web, reinforcing the cluster's role as a central node. So even though a cluster is a bound system, its influence extends into regions that are not fully bound, blurring the line between the system and its environment. This makes the concept of size more subtle. Is the size of a bound structure defined by the region where matter is fully bound? Or is it defined by the region where the structure has a significant influence? These are not the same thing, and they can differ by large factors. For example, a cluster's turnaround radius might be a few times larger than the region where most of its galaxies are found. Its region of gravitational influence might be larger still. So depending on how you define size, the same structure can have multiple, equally valid measurements. Another layer to this story comes from the role of time. Because light takes time to travel, when we observe a large structure, we are seeing different parts of it at different stages of its evolution. The near side is seen at a more recent time than the far side. So when we try to determine whether a structure is bound, we're often combining information from different moments in its history. This adds uncertainty to the picture. Scientists use models of how structures evolve over time to try to reconstruct a consistent view. They simulate how matter moves under gravity and expansion, starting from the early universe and moving forward to the present. By comparing these simulations to observations, they can estimate which regions are likely to remain bound and which are likely to drift apart. This is how they identify the bound cores of superclusters and distinguish them from the looser surrounding regions. Another interesting connection is to the concept of the cosmic horizon. There is a maximum distance from which light can reach us, given the age of the universe and the expansion of space. This defines the observable universe. Within this observable region, there are many bound and unbound structures. Beyond it, there may be more, but we cannot see them. So even the largest bound structures we can identify are limited by what we can observe. It is possible that, beyond our cosmic horizon, there are even larger bound systems or different arrangements of matter altogether. But these remain in the realm of speculation. Within what we can see, the largest bound structures appear to be massive clusters and the densest, most connected regions of superclusters. These systems represent the places where gravity has been most successful in resisting the pull of expansion. They are, in a sense, the strongholds of structure in an otherwise stretching universe. There is also a deeper, theoretical aspect to this limit. Some models of cosmology predict a maximum size for bound structures based on the properties of dark energy. If dark energy behaves like a constant energy density filling space, then there is a characteristic scale beyond which structures cannot remain bound. Observations of cluster sizes and dynamics can be used to test these models. If scientists were to find a bound structure larger than this predicted limit, it would challenge our understanding of dark energy and gravity. So the search for the largest bound structures is not just a matter of cataloguing impressive objects. It is a way of probing the fundamental laws that govern the universe. Another subtle point is that binding is not always all or nothing. Within a large structure, some parts may be tightly bound, while others are only loosely connected. Over time, the loosely connected parts may drift away, leaving behind a smaller, more tightly bound core. So the largest bound structures we see today may be in the process of shedding their outer layers, gradually shrinking in a gravitational sense, even as they may still appear large in a snapshot. This again emphasizes that size is a dynamic property, not a fixed one. There is a quiet elegance in this idea. The universe builds structures as large as it can given the time and the rules it has. Then, as conditions change, it allows some of those structures to loosen and fade while others remain. So when we talk about the larger structures bound by gravity, we're talking about a balance point in the universe's long evolution. A moment where gravity's reach and expansion's push are matched in a particular way. It can be grounding to think of gravity not as an absolute ruler, but as a participant in a larger conversation with expansion, dark matter and dark energy. The size of the largest bound structures is not just a fact, it is a story, written by the universe's history and its underlying physics. Beyond the scale where gravity can confidently claim a shared future for everything it touches, There are patterns in the universe that stretch so far and connect so loosely that they begin to feel less like single systems and more like extended conversations across space. These are the structures often called great walls, vast arrangements of galaxies and clusters that trace out enormous arcs, sheets, and chains in the cosmic web. They are not solid barriers, and they are not uniform objects in the everyday sense. They are regions where matter is more likely to be found, spread across distances so large that even light needs billions of years to cross them. To understand what a great wall is, it helps to return briefly to how we first learned to see the universe in 3 dimensions. For much of human history, the night sky appeared as a flat dome, with stars and galaxies sprinkled across its surface. It was only in the last century that astronomers developed reliable ways to measure the distances to galaxies, allowing them to build maps that extended not just across the sky, but deep into space. When these 3-dimensional maps began to include thousands, then millions of galaxies, something unexpected emerged. The galaxies did not fill space evenly. They formed chains. They traced out surfaces. They left behind vast empty regions. And in some places, these chains and surfaces connected into extended features that spanned hundreds of millions or even billions of light years. One of the first and most famous of these features is known as the Sloan Great Wall, discovered in data from the Sloan Digital Sky Survey. This structure stretches for roughly 1.4 billion light years and contains tens of thousands of galaxies. When it was announced, it immediately drew attention, not just for its size, but for what that size seemed to imply about the universe itself. At the time, many cosmological models predicted that, on the larger scales, the universe should look statistically smooth. There would be structures, of course, but if you zoomed out far enough, those structures would average out, and space would appear uniform. A feature as large as the Sloan Great Wall appeared to sit right at the edge of that expectation. It raised questions about whether our understanding of the early universe and the growth of structure was complete. Since then, other enormous features have been identified, such as the CFA Great Wall and the Hercules Corona Borealis Great Wall, though the latter remains a subject of debate. Some studies suggest it may span more than 10 billion light-years, nearly a tenth of the observable universe. Whether all of these are truly single, coherent structures, or just alignments of smaller features seen in projection is still an open question. And that brings us to the idea of physical coherence. When physicists talk about coherence in a system, they often mean that its parts are connected in a way that produces a shared, organised behaviour. In a coherent system, what happens in one part can influence what happens in another part in a predictable way. There is a sense of unity, even if the system is large and complex. A galaxy cluster is coherent in this sense. Its galaxies move within a shared gravitational field. They influence each other's orbits. The hot gas responds to the cluster's overall mass. Changes in one region can ripple through the system. A great wall, however, is different. The galaxies and clusters that make up a great wall are not necessarily moving together. They do not all orbit a common centre. They are not all gravitationally bound to each other. In many cases, the only thing they share is that they happen to lie along the same extended region of higher density in the cosmic web. This makes a great wall more like a pattern than a system. To see why, consider how filaments connect clusters. A filament might guide matter toward a cluster, creating a flow along its length. But that flow does not usually extend across the entire length of a great wall. Different segments of the wall can be connected to different nodes, with matter flowing in different directions. So while the wall appears as a continuous feature in a map, its internal dynamics can be quite fragmented. Another way to think about this is in terms of communication. For a system to be physically coherent, its parts need to be able to influence each other within a meaningful timescale. In a galaxy, signals, in the form of gravitational interactions or waves of gas and stars, can cross the system in tens or hundreds of millions of years. In a cluster it might take a few billion years, but that is still within the lifetime of the system. For a structure that spans 1 billion light-years, the situation is very different. Even light, the fastest signal possible, would take 1 billion years to travel from one end to the other. During that time, the universe itself is changing. Expansion is stretching space. Dark energy is becoming more influential. The conditions at one end of the structure are not the same as they were when the signal was sent, so any attempt at coordinated behaviour across such a vast distance is effectively impossible. The structure cannot act as a single, unified system in the physical sense. This is one of the reasons why some scientists hesitate to call great walls true objects. They are real patterns in the distribution of matter, but they lack the internal connectivity that defines a bound or coherent system. Another layer of complexity comes from how we observe these structures. When astronomers identify a great wall, they are often working with galaxy surveys that provide positions and distances for large numbers of galaxies. These distances are typically inferred from redshift, which, as we discussed earlier, is related to how fast a galaxy is moving away due to the expansion of the universe. Redshift-based distances are not perfect. They can be affected by the galaxy's own motion, not just by cosmic expansion. A galaxy moving toward or away from us within a cluster can appear slightly closer or farther than it really is. When you map millions of galaxies using these distances, small errors can add up. Features can appear more connected than they truly are, or separate features can appear to merge into a single, continuous structure. So part of the challenge in defining a great wall is distinguishing between a real, physically meaningful connection and a pattern created by the way we measure and display the data. This does not mean that great walls are illusions. The underlying overdensities they represent are real, but their exact size, shape, and continuity can depend on the methods used to identify them. Another important factor is the threshold used to define what counts as part of the structure. If you decide that a galaxy belongs to a wall if it lies in a region where the density is above a certain level, then changing that level can change the apparent extent of the wall. Lower the threshold, and the wall grows, connecting to neighbouring filaments and clusters. Raise it, and the wall shrinks, breaking into smaller segments. So in a very real sense, the boundary of a great wall is not a physical edge in space. It is a line drawn by the scientist based on a chosen definition. This brings us back to the idea of limits. The limits of physical coherence are not just about gravity versus expansion. They are also about our ability to define and measure patterns in a complex, continuous distribution of matter. On small scales, objects are clearly defined. A star is a star. A planet is a planet. On intermediate scales, systems like galaxies and clusters are well defined, because their parts are bound together and interact strongly. On the larger scales, structure becomes more statistical. It is about regions of higher or lower density, about trends and patterns rather than about discrete self-contained systems. A great wall sits in this statistical regime. It is a prominent feature, but not a closed system. There is also a temporal aspect to this. The parts of a great wall are not all at the same stage of evolution. The light from one end of the wall might be billions of years older than the light from the other end. When we look at the wall as a whole, we are seeing a time-lapse of cosmic history stretched across space. This means that the structure we observe has never existed in exactly the form we see. It is a composite of different moments in time. This further complicates the idea of coherence. A system that does not exist as a single, simultaneous entity is hard to treat as a single physical object. Another interesting way to approach this is through simulations. When scientists simulate the growth of structure in the universe, they often see long, extended filaments and walls form naturally. These features arise from the way matter flows along the dark matter network and accumulates at intersections. In simulations, it is possible to track the motion of matter over time and see which parts of a structure remain connected and which drift apart. These studies generally find that while great walls can be visually impressive and persistent in a statistical sense, They are not usually bound as single systems. Different segments often have different futures. Some will fall into clusters, others will be pulled away by expansion. So the wall is more like a snapshot of a flow pattern than a permanent unified object. There is also an interesting connection to the concept of the cosmological principle, the idea that the universe is, on large scales, homogeneous and isotropic, meaning it looks roughly the same in all directions and from all locations. The existence of very large structures like great walls tests this principle. If the universe were perfectly homogeneous on all scales, such features would not exist. The fact that they do exist suggests that the scale at which the universe becomes truly smooth is very large, perhaps larger than some of the biggest structures we have identified. However, when scientists analyse the distribution of matter statistically, they still find that beyond a certain scale, the universe does appear to approach uniformity. The great walls and filaments, while large, are still fluctuations within a broader, nearly uniform background. So the limits of physical coherence are not just about how big a structure can be, but about how big a deviation from uniformity can persist. Another subtle aspect of this story is how great walls relate to the idea of influence. A bound system like a cluster can influence the motion of matter throughout its domain. A great wall, because it is not bound as a whole, does not exert a unified influence across its entire length. Instead, influence is local. Each cluster or dense region within the wall influences its immediate surroundings. The wall as a whole does not act as a single gravitational entity. So in terms of physical cause and effect, the wall is more like a collection of overlapping zones of influence than a single dominant source of gravity. This distinction matters when we think about the largest object in the universe. If we define an object as something that has a unified physical identity, a shared gravitational field and a coherent internal dynamic, then great walls may not qualify despite their enormous size. If we define an object as a continuous pattern in the distribution of matter, then great walls are among the largest examples we know. Both definitions are reasonable. They simply emphasize different aspects of what it means to be a thing in an expanding universe. There is also a practical side to this. When scientists catalogue structures, they often give them names and boundaries, because that makes them easier to talk about and study. A named wall, a named supercluster, a named filament becomes a reference point in the vast complexity of cosmic structure. But these names and boundaries are tools, not absolute truths. They help organise our understanding, but they do not necessarily correspond to sharp divisions in the universe itself. Another way to think about great walls is as transitions. They mark regions where the density of matter changes more rapidly than average. They separate large voids. They connect major nodes of the cosmic web. In this sense, they are like coastlines in the distribution of matter, places where one kind of region gives way to another. This perspective highlights their role in the overall architecture of the universe, even if they are not unified systems in the strict physical sense. As the universe continues to evolve, the fate of these structures will be shaped by the balance between gravity and dark energy. Over time, expansion will stretch space between the segments of a great wall. The connections that make it appear continuous today may become weaker. Parts of the wall may drift into isolation, becoming associated with different bound systems or none at all. So the great walls we see now may be temporary features in the long history of the universe, prominent at this moment, but destined to fade as the cosmic web becomes more fragmented. There is something quietly profound in that idea. The largest patterns we can observe are not permanent monuments. They are stages in a process, shaped by initial conditions, physical laws, and the passage of time. They exist not as fixed objects, but as evolving configurations of matter and space. So when we talk about the limits of physical coherence, we're really talking about the point where our everyday intuition about objects and systems gives way to a more fluid, statistical view of the universe. At that scale, the universe is less about things and more about patterns, less about boundaries and more about gradients, less about unity and more about connection. There is a moment when you follow the chain of size far enough, where the question almost turns back on itself. Instead of asking what the biggest structure inside the universe might be, you begin to wonder whether the universe itself can be placed in the same category as the things it contains. Can it be treated as an object in the same sense as a star, a galaxy, or even a great wall, or is it something fundamentally different, something that does not fit inside the same conceptual frame at all? To approach this, it helps to step carefully through what physicists usually mean when they talk about an object. In most areas of physics, an object is something that exists within space and time. It has a location. It can move. It can interact with other things. You can describe its properties such as mass, energy, shape and motion relative to a surrounding environment. A planet orbits a star. A star moves through a galaxy. A galaxy drifts within a cluster. In each case, there is a larger context in which the object exists and within which its behaviour can be described. When you try to apply this same idea to the universe as a whole, the situation changes. By definition, the universe includes all of space and time, all matter and energy, and all the physical laws that govern them. There is nothing outside it that you can refer to as a background or an environment. There is no larger stage on which the universe itself sits. So the first difficulty in calling the universe an object is that it does not have an external reference frame. In physics, motion is always described relative to something else. A train moves relative to the tracks. The Earth moves relative to the Sun. The Sun moves relative to the centre of the Milky Way. But the universe as a whole does not move relative to anything outside it, because there is nothing outside it to move relative to. This means that some of the most basic properties we use to describe objects such as position and velocity do not apply to the universe in a straightforward way. Another difference lies in boundaries. An object usually has an edge, even if that edge is fuzzy. A star has a surface where its gas becomes thin enough to let light escape. A galaxy has a region beyond which its stars and dark matter become sparse. Even a great wall has a region where its density blends into the surrounding voids. The universe, as far as we can tell, does not have a boundary in the same sense. When we talk about the observable universe, we're talking about the region of space from which light has had time to reach us since the beginning of cosmic expansion. That boundary is not a physical edge. It is a limit set by time and the speed of light, not by the end of space itself. Beyond the observable universe, there may be more space, more galaxies, more structures. We simply cannot see them, because their light has not reached us yet, and may never reach us if the expansion of the universe continues to accelerate. So the universe does not present itself as a contained thing with a clear outline. It is instead an open-ended system, at least from our current point of view. This leads to an important distinction between the universe and everything inside it. An object inside the universe can, in principle, be separated from its surroundings. You can imagine isolating a planet from its star, or a galaxy from its cluster, even if doing so would take an enormous amount of energy. The idea of separation makes sense. With the universe as a whole, separation loses its meaning. You cannot take the universe out of its context because there is no context beyond it. So in this sense, the universe is not an object in the usual physical meaning of the word. It is the totality of all objects and all contexts. However, physicists still study the universe as a system. This is the field of cosmology, which treats the universe as a whole as something that can be described by equations, models, and measurable parameters. In this approach, the universe is characterized by things like its average density of matter and energy, its rate of expansion, its overall geometry, and its composition in terms of ordinary matter, and dark energy. So while the universe may not be an object in the everyday sense, it is a subject of physical description. One of the key ideas in cosmology is that On the larger scales, the universe is homogeneous and isotropic. This means that if you average over large enough regions, the universe looks roughly the same in all directions and from all locations. This assumption, known as the cosmological principle, allows physicists to write down relatively simple equations that describe the overall behaviour of the universe, even though the details on smaller scales can be very complex. These equations, derived from general relativity, describe how the universe expands over time in response to its content of matter and energy. In this framework, the universe has properties that are often associated with objects, such as size, age, and shape. For example, the universe has an age, which we estimate to be about 13.8 billion years, based on measurements of the expansion rate and the cosmic microwave background. It also has a characteristic scale, which is often described in terms of the observable universe, about 93 billion light-years in diameter. It even has a geometry, which can be described as flat, open, or closed, depending on how space is curved on large scales. Current observations suggest that the universe is very close to flat, meaning that parallel lines remain parallel, and the usual rules of geometry apply on the larger scales we can measure. So in this cosmological sense, the universe is treated as a single coherent system with global properties, but there is a subtle difference between a system and an object. A system can be defined by the relationships between its parts and the rules that govern them, without necessarily being a thing with a boundary and an external environment. The universe, in this view, is the ultimate system. It is the set of all physical relationships. Another way to approach this question is through the concept of energy. In physics, an object usually has a well-defined total energy. You can add up its kinetic energy, its potential energy, its internal energy, and so on. For the universe, this is more complicated. In general relativity, defining a total energy for the entire universe is not straightforward, especially if the universe is infinite or has no boundary. The usual methods for calculating energy rely on being able to define what is happening at infinity, which does not make sense when you're talking about everything that exists. Some cosmological models suggest that the total energy of the universe might be zero, with the positive energy of matter and radiation balanced by the negative energy associated with gravity. This is an intriguing idea, but it is not something that can be directly measured. So even at the level of energy, the universe does not behave like a typical object. There is also the question of causality. Within an object or a system, different parts can, in principle, influence each other given enough time. Signals can travel, forces can propagate, and changes in one region can eventually affect another. For the universe as a whole, this is not necessarily true. Because the universe is expanding, and because that expansion is accelerating, there are regions of space that are so far away from each other that they are causally disconnected. Light or any other signal sent from one region will never reach the other. This creates cosmic horizons, boundaries of influence rather than boundaries of space. So the universe as a whole is not a fully connected system in the sense that all its parts can interact with each other. It is a collection of regions, some of which are forever out of causal contact. This challenges the idea of the universe as a single coherent object. Another perspective comes from thinking about time. An object usually exists within time. It has a past, a present, and a future. It may change, but the flow of time itself is something that happens to it. In cosmology, time is part of the system being described. The universe is not just something that exists in time. It is something in which time exists. The Big Bang is often described as the beginning of time as well as the beginning of space. In this view, there is no before the universe, in the same way that there is a before a star forms or a galaxy merges. So the universe is not just an object with a history. It is the context in which all histories occur. This makes it qualitatively different from anything inside it. There is also a deeper theoretical layer to this question, which comes from attempts to combine general relativity and quantum mechanics. In some approaches to quantum gravity, the universe itself is treated as a kind of quantum system. There are models in which the universe has a wave function, describing the probabilities of different possible configurations of space and matter. In this framework, the universe can, in a mathematical sense, be treated like an object, with a state that evolves according to certain rules. However, this is very far from everyday intuition, and it raises many unresolved questions, such as what it means to observe the universe when there is nothing outside it to serve as an observer. So even at the most fundamental level, the status of the universe as an object is ambiguous. Another way to think about this is to consider how we use language. When we say the universe, we often mean different things in different contexts. Sometimes we mean the observable universe, the region we can see. Sometimes we mean the totality of everything that exists, including regions beyond our horizon. In the first sense, the universe can be treated a bit more like an object. The observable universe has a boundary, even if it is not a physical one. It has a size, a shape, and a content that we can, in principle, measure and describe. In the second sense, the universe is more like a concept than a thing. It is the category that includes all things. This dual use of the word can make the question feel more confusing than it needs to be. If you ask whether the observable universe is an object, the answer can be, in a practical sense, yes. It is a region of space-time with measurable properties, and scientists study it as a whole. If you ask whether the total universe is an object, the answer becomes much less clear, because it lacks the features that usually define an object, such as boundaries, an external context, and full internal connectivity. There is also a philosophical angle to this, which has been debated for centuries. Some philosophers have argued that the universe is a substance, something that exists in its own right, independent of the things within it. Others have argued that the universe is just the sum of all its parts, and that there is nothing more to it than that. In physics, this debate takes on a practical form in questions about whether the laws of physics themselves are part of the universe, or something that applies to it from outside. Most physicists would say that the laws of physics are part of the universe. They describe regularities in how matter and energy behave. They are not external rules imposed from beyond. So in that sense, the universe is not just an object governed by laws. It is the system in which the laws themselves are embedded. Another interesting way to approach this is through the idea of self-containment. An object is usually something that can, at least in principle, be fully described by specifying its properties and its relationships to other objects. The universe, however, includes all those relationships. There is no other to relate it to, so any description of the universe is necessarily internal. We are using parts of the universe, including ourselves and our instruments, to describe the whole. This creates a kind of self-reference that does not occur when we study smaller objects. For example, when you study a star, you are outside the star. You use light that leaves the star and reaches your telescope. You are not part of the star's internal system. When you study the universe, you are part of the system you're studying. Your observations, your instruments, and your theories are all physical processes happening within the universe. This makes cosmology unique among the sciences. Another layer to this question comes from the idea of multiple universes, sometimes called the multiverse. Some theories of physics, particularly those related to cosmic inflation and string theory, suggest that what we call the universe might be just one region within a much larger ensemble of regions, each with its own physical properties. If this were true, then our universe might be an object within a larger context. However, these ideas are highly speculative and not currently testable in a direct way. So for now, they remain more in the realm of theoretical exploration than empirical science. Within what we can observe and measure, the universe appears to be a closed system, with no access to anything beyond it. This brings us back to the practical side of the question. In the context of asking about the largest object ever found in the universe, treating the universe itself as an object can feel like a kind of shortcut, a way of ending the search by definition rather than by measurement. If the universe is the largest thing, then the question becomes trivial. But the spirit of the question is usually about finding the largest structure within the universe, something that can be compared to other structures in terms of size, mass, or extent. In that sense, the universe itself sits in a different category. It is not one of the contestants in the contest of size. It is the arena in which the contest takes place. There is a certain calm in recognizing this distinction. It means that no matter how large a structure we find, no matter how far our maps extend, there will always be a broader context in which it exists, even if that context is simply the rest of the universe we have not yet observed. So the question of whether the universe is an object becomes less about finding a final answer, and more about clarifying how we use our concepts. Objects, in the usual physical sense, are things within the universe that have boundaries, interactions, and shared dynamics. The universe itself is the totality of those things and the stage on which their interactions play out. It can be described, modelled, and studied as a whole, but it does not fit neatly into the same category as the structures it contains. As this idea settles, it naturally points toward a more reflective perspective. When you look at the largest walls, filaments, clusters, and galaxies, you're looking at patterns inside a system that is, in a very real sense, beyond complete grasp. We can map parts of it. We can measure its expansion. We can infer its composition. But we cannot step outside it to see it from the outside. So our understanding of the universe is always an inside view, shaped by the limits of observation and the tools of theory. Long before you reach the edges of what can be mapped or named, before the language of clusters, filaments, and walls begins to lose its sharpness, there is a quieter shift that happens in the way the universe is understood. Scale stops being just a measure of size and starts becoming a lens, something that changes how space, time, and even the idea of reality itself appear when you look through it. Moving from the small to the large is not simply a journey across distance. It is a journey across different ways the same physical laws express themselves. At the smallest scales we can currently probe, reality is described in terms of particles, fields, and probabilities. Electrons do not have precise positions in the way a pebble on the ground does. They exist as patterns of likelihood, governed by wave functions and uncertainty. Energy comes in discrete packets. Interactions happen through the exchange of tiny carriers, like photons and other force particles. At these scales, time and space behave in ways that are not intuitive. Events can be correlated across distance in ways that seem to defy simple cause and effect. Measurement itself becomes part of the system, influencing what is observed. As you move outward in scale, these strange quantum behaviours begin to average out. Collections of particles form atoms, atoms form molecules, molecules form solids, liquids, and gases. The probabilistic nature of individual particles becomes less noticeable when you are dealing with trillions of them at once. This transition is not marked by a sharp boundary. There is no single point where the universe suddenly stops being quantum and starts being classical. Instead, there is a gradual blending, a smoothing of uncertainty into something that looks more stable and predictable. By the time you reach the scale of everyday objects, the world behaves in a way that feels solid and continuous. A chair stays where it is. A planet follows a path. A clock ticks at a steady rate. But even here, scale is still shaping what you see. Gravity, for example, is an extremely weak force at the level of individual particles. Between two electrons, the gravitational attraction is negligible compared to the electromagnetic force. But as you move to larger and larger collections of matter, gravity begins to dominate. A mountain holds itself together because of gravity. A planet forms because of gravity. A star ignites because gravity compresses its core to the point where nuclear fusion can begin. So at larger scales, gravity becomes the organizing principle. When you step up again to the scale of galaxies and clusters, Gravity is not just holding things together, it is shaping the architecture of the universe. It is carving out wells and ridges in space-time, guiding the flow of matter along filaments and into dense nodes. At this level, space and time are no longer passive backgrounds, they become dynamic. According to general relativity, mass and energy tell space-time how to curve, and curved space-time tells matter how to move. This relationship becomes especially important on large scales, where the cumulative mass of stars, gas and dark matter can significantly bend the geometry of space. So a galaxy cluster is not just a collection of galaxies in a pre-existing space. It is a region where space itself is shaped by the presence of mass. Light passing through this region follows curved paths. Time passes slightly more slowly deep in the gravitational well. This is a different way of thinking about reality. Instead of objects moving through a fixed stage, the stage itself is part of the play. As you move to even larger scales, another shift occurs. On the scale of the cosmic web, the universe begins to look less like a collection of individual objects and more like a continuous medium with variations in density. Filaments and voids are not separate things in the way a star and a planet are separate. They are regions of higher and lower concentration within a single, connected distribution of matter and energy. At this scale, the language of objects becomes less precise. It is often more useful to talk about fields, flows, and patterns. Matter flows along filaments. Voids expand. Clusters grow by accretion. These are not the behaviours of isolated things. They are the behaviours of a system as a whole. This perspective changes how time is experienced, at least conceptually. On human scales, time is something that passes uniformly, measured by clocks and calendars. On the scale of stars, time becomes the story of life cycles measured in millions or billions of years. On the scale of galaxies and clusters, time becomes the story of structure formation, measured in the slow assembly of mass across cosmic history. When you look at a galaxy billions of light years away, you're seeing it as it was billions of years in the past. The farther away you look, the younger the universe appears. So space becomes a kind of time machine. Distance and history become intertwined. At the largest scales, this connection between space and time becomes even more pronounced. The expansion of the universe means that the distance between two regions of space is not fixed. It changes over time. This is not because galaxies are simply moving through space like cars on a road. It is because the space itself between them is stretching. So when you talk about the size of the universe, you're also talking about its age and its future. A structure that is a certain size today was smaller in the past and may be larger in the future. But whether it will remain a single structure depends on how gravity and expansion interact over time. This means that scale is not just a spatial concept, it is a temporal one as well. Another layer to this is the role of dark energy. On small scales, dark energy has no noticeable effect. The gravitational pull between nearby masses is far stronger than the gentle push of cosmic expansion. But on the larger scales, dark energy becomes dominant. It determines how fast the universe expands. It sets a horizon beyond which regions of space will never be able to influence each other. So at the larger scales, the structure of reality is shaped not just by what is present, but by how space itself behaves. This brings a subtle shift in how causality is understood. In everyday life, it is usually assumed that any two things can, in principle, affect each other, given enough time. But in an expanding universe with dark energy, this is not true. There are regions of space that are so far apart and being carried away from each other so quickly that no signal sent from one will ever reach the other. They are permanently causally disconnected. So reality, at the larger scales, is not a single, fully connected whole. It is a collection of regions, each with its own causal past and future. This challenges the intuitive idea that the universe is a single, unified system in which everything is ultimately linked. Another perspective comes from thinking about measurement. At small scales, measurement can be very precise. You can measure the position of a particle, the length of an object, the frequency of a light wave. As you move to larger scales, measurement becomes more indirect. You cannot stretch a tape measure across a galaxy. You infer distances from brightness, redshift, and models of cosmic expansion. At the larger scales, even these methods become less certain. You're dealing with averages, statistical patterns, and assumptions about the overall behaviour of the universe. So scale also changes the nature of knowledge. The farther out you go, the more your understanding relies on inference rather than direct measurement. This does not make it less real, but it does make it more abstract. Another important aspect of scale is how it reveals different symmetries and patterns. On small scales, the universe can look messy and irregular. Rocks are jagged, clouds are lumpy, stars are scattered in complex patterns. On larger scales, patterns emerge. Galaxies form spirals and ellipses. Clusters form roughly spherical or elongated shapes. Filaments and voids form a web-like structure. On the larger scales, the universe appears to approach uniformity. The detailed patterns average out, and what remains is a nearly smooth distribution of matter and energy. This progression from irregularity to pattern to uniformity is a common theme in physics. It reflects the way that complex systems can exhibit different behaviours at different scales. In this sense, reality is layered. Each layer has its own rules, its own dominant forces, and its own typical structures. Quantum mechanics dominates the smallest scales. Electromagnetism and chemistry dominate the scale of atoms and molecules. Gravity dominates the scale of stars, galaxies, and beyond. Dark energy shapes the largest scales of all. These layers are not separate universes. They are different ways of describing the same underlying reality, depending on what you're looking at and how closely. This layered nature of reality is one of the things that scale makes visible. Another way to think about this is in terms of emergence. Emergent properties are features of a system that are not obvious from the behaviour of its individual parts. For example, temperature is an emergent property. A single molecule does not have a temperature. Temperature only makes sense when you are dealing with a large collection of molecules and can talk about their average motion. Similarly, a single star does not define a galaxy. A galaxy is an emergent structure that arises from the collective behaviour of billions of stars and clouds of gas within a dark matter halo. The cosmic web is an emergent structure that arises from the collective behaviour of countless galaxies and dark matter clumps under gravity and expansion. So as you move up in scale, new kinds of reality appear, not because new laws are introduced, but because the same laws produce different kinds of behaviour when applied to larger and more complex systems. This idea can be grounding. It suggests that the universe is not a collection of disconnected phenomena, but a continuous process, where simple rules give rise to rich and varied patterns across an enormous range of scales. Another subtle point about scale is how it changes the role of chance and necessity. At the level of individual particles, events can be genuinely probabilistic. You can only predict the likelihood of a certain outcome, not the outcome itself. At the level of large systems, those probabilities average out, and behaviour becomes more predictable. You cannot predict the motion of every molecule in a gas, but you can predict the pressure and temperature of the gas as a whole. At the level of the universe, some aspects seem fixed by initial conditions and fundamental constants. The overall expansion rate, the amount of dark matter, the strength of gravity, and the properties of particles all shape what kinds of structures can form. So scale reveals a spectrum between randomness and order, between chance events and large-scale regularities. There is also a personal dimension to this. Human experience is tied to a very narrow band of scales. We live in a world where objects are measured in meters, time is measured in seconds, and energy is measured in amounts that fit comfortably within our daily lives. When you move far outside this band, either to the very small or the very large, intuition begins to fail. You need mathematics, models, and imagination to bridge the gap. In that sense, thinking about cosmic scale is an exercise in expanding perspective. It invites you to consider that the way the world feels at your own scale is just one version of reality among many, shaped by the particular size and timescale of the systems you are part of. Another interesting aspect of scale is how it affects the concept of identity. At small scales, identity is tied to individual particles. An electron is an electron. A proton is a proton. At larger scales, identity becomes more flexible. A star can lose mass and still be considered the same star. A galaxy can merge with another and still be considered a galaxy. At the scale of clusters and filaments, identity becomes even more fluid. Structures grow, merge, and change shape over time. Their boundaries are fuzzy. Their names are labels we apply for convenience. So scale reveals that identity, like size, is not always a fixed property. It can depend on how you choose to describe and categorize what you see. There is also a connection to the idea of limits. At very small scales, there may be a fundamental limit to how precisely you can measure things, set by quantum mechanics. At very large scales, there may be a limit to how much of the universe you can ever observe, set by the speed of light and the expansion of space. So reality, at both ends of the scale, is bounded by horizons of knowledge. Within those horizons, there is a vast range of structures, patterns, and behaviours. Beyond them, there may be more, but it is inaccessible, at least in principle. This can be a quiet reminder that understanding is always partial. Even with the most powerful telescopes and the most refined theories, there will always be aspects of the universe that lie beyond direct reach. Another perspective on scale is how it shapes the way questions are asked. On small scales, you ask what something is made of. What particles, what forces, what interactions. On larger scales, you ask how things are arranged. What patterns, what flows, what histories. On the larger scales, you begin to ask why the universe has the properties it does. Why these laws, these constants, this expansion? So scale guides not just what you see, but what you wonder about. This progression of questions mirrors the progression of structure in the universe, from particles to patterns to principles. There is a kind of continuity in this. The same physical laws that govern the fusion in a star's core also govern the growth of a galaxy cluster. The same expansion that stretches the space between distant galaxies also shapes the ultimate fate of the largest structures. So when you look at the universe through the lens of scale, you're not just looking at different sizes of things, you're looking at different expressions of the same underlying reality. This can be a steadying thought. It suggests that the complexity and vastness of the universe are not signs of chaos, but of a deep and consistent order, one that unfolds in different ways depending on how much of it you take in at once. After travelling outward through layers of scale that stretch far beyond ordinary intuition, there is a natural tendency to feel suspended, as if perspective itself has drifted away from familiar ground. The universe, when viewed at its largest scales, can feel distant and abstract, full of numbers too large to picture and structures too vast to hold in a single thought. So this return is not a retreat from physics or from understanding. It is a gradual reorientation, a way of letting those enormous ideas settle back into a frame where they can coexist with everyday experience without tension. One of the first things that becomes clear when you step back from the edge of physical existence is that scale does not cancel meaning. The fact that galaxies stretch across hundreds of thousands of light years, or that filaments span hundreds of millions, does not make smaller scales insignificant. Instead, it places them within a larger continuity. Every level of structure exists because the levels below it behave in certain ways, and every level above it creates the conditions in which it exists. The atoms in your body were assembled in stars that lived and died billions of years ago. Those stars formed inside galaxies shaped by dark matter. those galaxies occupy filaments and clusters whose growth depended on the earliest fluctuations in the young universe. None of these steps replaces the others. They stack quietly and persistently across time and scale. From this angle, the universe does not feel like a place where the small is overwhelmed by the large. It feels more like a system where size is relational. A star is small compared to a galaxy, but immense compared to a planet. A galaxy is small compared to a cluster, but vast compared to any structure humans can directly interact with. Scale does not diminish importance, it changes context. Another realization that often emerges during this return is that physical limits are not failures of understanding. They are features of the universe itself. There are distances light cannot cross within the lifetime of the cosmos. There are regions that will never exchange information. There are structures that can be mapped statistically but not treated as unified systems. None of this points to a breakdown in physics. It reflects the way space, time, and causality are woven together. In everyday life, it is common to assume that if something exists, it must be fully accessible in principle. But the universe does not operate on that assumption. Accessibility depends on location, timing, and the rate at which space itself evolves. Some information is simply out of reach, not because it is hidden, but because the universe does not permit its retrieval. This can feel unsettling at first, but it can also be stabilizing. It means that not knowing everything is not a temporary condition waiting to be resolved. It is part of the structure of reality. From here, it becomes easier to let go of the need for a single largest answer. When people ask about the largest object ever found in the universe, they're often looking for something definitive, something that can be named and measured and placed at the end of a list. What the physics reveals instead is a set of overlapping limits. The largest bound systems, the largest coherent patterns, the largest observable regions. Each answer is correct within its own frame, and none of them stand alone. This layered outcome mirrors the layered nature of the universe itself. There is no single scale at which everything resolves cleanly. Instead, there are transitions, thresholds, where one kind of description becomes less useful and another takes over. Stars yield to galaxies. Galaxies yield to clusters. Clusters give way to filaments. Filaments dissolve into statistical structure. And eventually the idea of an object gives way to the idea of a whole. That does not make the earlier questions pointless. It gives them depth. As attention shifts back toward more familiar scales, something else becomes noticeable. The same physical laws that govern the larger structures are quietly at work everywhere. Gravity still pulls, energy still flows, time still advances locally even as it stretches globally. There is no sharp boundary where cosmic physics ends and everyday physics begins. They are the same physics, expressed differently depending on scale. A falling object near Earth and a galaxy orbiting within a cluster are both responding to gravity. The equations differ in detail, but the underlying principle is shared. Light leaving a distant galaxy and light entering your eyes are both travelling through curved space-time, influenced by mass along the way. The difference lies in distance and accumulation, not in kind. This continuity can be grounding. It means that the universe is not divided into separate realms of relevance. The same reality that produces great walls also produces the ground beneath your feet. Another aspect of this return involves time. Cosmic timescales can make human lifetimes feel vanishingly brief. Stars live for billions of years. Galaxies evolve over spans far longer than civilization has existed. From that perspective, human activity can seem like a fleeting spark. But this comparison only makes sense if all timescales are treated as competing measures of significance. Physics does not assign value that way. Duration is not importance. A process that lasts a fraction of a second can be decisive. A process that takes billions of years can be gentle and incremental. Human experience unfolds on a timescale where seconds, hours, and years matter. that scale is not invalidated by the existence of longer ones. It is simply one layer among many. In fact, the very possibility of reflecting on cosmic scale depends on processes that operate quickly and locally. Neural signals move in milliseconds. Light crosses a room in a fraction of a second. Instruments respond rapidly enough to record signals from space. Without these fast processes, the slow story of the universe would remain inaccessible. So the ability to think about the largest structures is itself a product of smaller, faster ones. There is also a subtle shift in how reality feels when you come back from these extremes. The universe, when considered only in terms of its larger scales, can feel impersonal, almost indifferent. But when those scales are folded back into a layered view, something else appears. The universe becomes a place where complexity is not an accident, but an outcome. Simple rules, applied consistently across vast spans of time and space, give rise to stars, chemistry, planets, and eventually observers capable of asking questions about size and meaning. This does not require purpose or intention in a human sense. It only requires consistency and time. From that perspective, the existence of structures large enough to challenge our definitions is not surprising. Given enough space and enough time, patterns will emerge that push against the limits of classification. This brings attention back to the role of definitions themselves. Much of what makes the largest structures feel strange is not their size alone, but the way they resist being placed into familiar categories. They're too large to be objects in the usual sense, but too structured to be treated as mere randomness. They sit between concepts, forcing language and intuition to stretch. That stretching is not a flaw. It is how understanding grows. Physics often advances not by finding neat answers, but by discovering where existing concepts stop working cleanly. The idea of a particle breaks down at quantum scales. The idea of a rigid object breaks down at relativistic speeds. The idea of a single largest object becomes ambiguous at cosmic scales. Each of these breakdowns leads to deeper descriptions rather than confusion. As this return continues, there is also room to notice how the universe accommodates quietness as well as grandeur. For every massive cluster or luminous wall, there are vast voids where little happens, regions where matter is sparse, interactions are rare, and changes slow. These voids are not failures of structure, they are part of it. In fact, without voids, filaments would not stand out. Without emptiness, density would have no contrast. This balance between presence and absence exists at all scales. Between stars lie stretches of space far emptier than anything humans encounter. Between galaxies lie even greater expanses. And yet, these empty regions play essential roles in shaping motion and flow. So even at the larger scales, the universe is not defined only by what is there, but also by what is not. Bringing this back toward more immediate experience, there is a parallel. Moments of quiet, pauses between activity, often provide structure to daily life. They separate events, give shape to memory, and allow reflection. In that sense, voids are not foreign to human experience. They are familiar in a different form. Another point that becomes clearer during this return is that knowledge of the universe is cumulative and provisional. Every map of large-scale structure depends on current instruments, current surveys, and current models. As measurements improve, boundaries shift, structures are reclassified, new patterns emerge. What is considered the largest today may not hold that title forever, not because the universe changes rapidly, but because understanding deepens. This does not undermine the value of current knowledge. It places it in context. Science is not a catalogue of final answers. It is an ongoing refinement of descriptions. So the question of the largest object ever found is not something that closes neatly. It opens into a broader understanding of how size, coherence, and definition interact. There is also a quiet reassurance in realizing that no matter how large the universe appears, it remains governed by rules that are intelligible. Complex, yes. Challenging, certainly, but not arbitrary. The The same equations that describe the expansion of space can be tested against observations. The same models that predict filament formation can be compared with galaxy surveys. Even when answers are incomplete, they are constrained. This reliability is part of what allows the mind to rest rather than race when contemplating vastness. The universe is not chaotic in the sense of being unknowable. It is structured in ways that reward patience. As attention settles further inward, it becomes easier to hold two perspectives at once. On one hand, the universe is immense, filled with structures so large that they strain language. On the other hand, experience unfolds locally, quietly, within a narrow slice of scale and time. These perspectives do not compete, they coexist. You can know that light from distant galaxies has travelled for billions of years, and still feel the immediate presence of the space around you. You can understand that clusters are gravitational wells, and still notice the steady rhythm of your own breathing. Physics does not demand that one awareness replace the other. In fact, one of the strengths of human cognition is the ability to shift scale mentally without losing coherence. This is part of why science can be calming rather than overwhelming when approached gently. It does not require constant focus on extremes. It allows movement back and forth, outward and inward. Another aspect of this return is recognizing that questions about size are, at their core, questions about relationship. Large compared to what? Bound in relation to which forces? Coherent over what timescale? Observable from where? Once those relationships are made explicit, the mystery becomes more navigable. The universe stops feeling like an ungraspable infinity and starts feeling like a structured space with regions of clarity and regions of uncertainty. Uncertainty itself becomes less threatening when it is recognized as bounded. There are things we do not know, but we often know where those gaps are and why they exist. That kind of uncertainty is different from confusion. It has shape. As this sense of shape settles, the journey from the edge of physical existence no longer feels like a fall back into smallness. It feels like a return to balance. The universe does not demand constant attention to its larger scales. It allows attention to rest where it is most useful, while still being open to expansion when curiosity arises. So the larger structures remain where they are, vast and distant, doing what they do regardless of observation. They do not press inward. They do not require resolution. They are simply part of the broader picture, one layer among many. And from here, without closing anything off, without drawing a final boundary, attention can remain gently suspended between scales, not fixed on the edge, not withdrawn from it either, just aware that the universe is large, structured and ongoing, and that understanding it is less about reaching an endpoint and more about learning how to move comfortably within its many layers.